And we are going to start with the keynote speaker, Francisco Ocampo.
Esto funciona así, para adelante, esto se cruza para atrás, y el láser lo apretas y viene el láser. ¿Lo apretas? No me está funcionando el láser. Ahí está, ahorita sí. Ahora sí. Ahora sí. Es digital, es como el... ¿Lo están apretando? Sí.
Hello, everyone. Good morning. Good morning, everyone. Thanks for being here. I'm glad, and it's an honor to be here in this fourth symposium, Latin American Symposium on Water Waves. My name is Paco Ocampo Torres from Ensenada in Mexico, and I'm affiliated to CEMIE-OCÉANO, which is a national program for marine energy. I'd like to express and announce my co-authors. Of course, the work I'm going to present is not my own work. A little help from my friends are needed. These are Pedro Osuna from the Physical Oceanography Department in CICESE, Nicolás Rascle. Now he is at IFREMER and used to be with us some time ago. Héctor García Nava from the University of Baja California, and Guillermo Díaz Méndez and Bernardo Esquivel Traba, researchers associated to CIGOM at CICESE. I'd like to say that CIGOM is a national project for studying the dynamics of the Gulf of Mexico, and of course the support from CONACYT, the National Research Council, and the Ministry of Energy are acknowledged. Okay, the title of the presentation is Ocean Surface Wave Modulation Processes Under Atmospheric Front Conditions. Please consider this presentation as a progress report. This is undergoing research, and at least I'm going to show you some details of the buoy network that we have built and we operated for a few years through this national project for the Gulf of Mexico. I'd like to mention that we are more focused in this presentation to spar buoys to study ocean surface wave dynamics. This is a type of buoys that have been developed by the group of Graver and Donnellan in the University of Miami, but we have built some of those with our own electronic design. We like to focus on air-sea interaction and surface currents. This is understanding what happened in the upper ocean and lower atmosphere. Essentially, focus in this Gulf of Mexico project, taking into account the needs for action whenever an accident occurring, meaning oil spills or something like that. So we are trying to understand air-sea interaction in the context of oil dispersion or contaminants dispersion. With this type of buoys, it is possible to obtain the directional wave spectrum, and we study its evolution. And it is now well recognized the directional wave spectrum is essential to determine surface currents, especially at the very surface. And we would like to address, at least in the near future, what happens under varying wind conditions. This is because we have usually atmospheric fronts passing by the Gulf of Mexico. In this presentation, I will tell you something of the analysis we are doing using ocean surface synthetic aperture radar images in order to retrieve information regarding the waves and else. So, as a tail of the Gulf of Mexico buoy network, this project supported by CONACYT and Ministry of Energy It's important to mention that we developed two types of buoys. We developed and built and operated two types of buoys. Coastal oceanography buoy, BOC, we call them for Spanish acronym. And we deployed several and operated from between 2016 and 17. We also build and operate another box to operate 2018 and 19. And we managed to deploy 3 BOM, which is these spar buoys, again, between 2018 and 19. The idea is that we are using these enhanced spar buoys to study ocean surface wave dynamics. And regarding the coastal oceanography buoys, the box, we refer to this article where some description of the first generation of box is given. So we can see here the kind of network that we managed to build, not necessarily simultaneous in this particular time, but at least focus our attention in the BOM deployed in 2018 and 19, and we managed to work with these three, BOC 2 in Veracruz and BOC 3 in Arrecife Alacranes. And we will explain a little bit more on regarding BOM 1 in the Perdido area, which is called this zone in front of Tamaulipas coastline in Mexico. The small buoys, the coastal oceanography buoys, are of this type. Nothing extraordinary, probably 3 meters in height and about 2 meters in diameter. And they are limited in terms of sensors. We have a CTD, meteorological stations, sensors for CO2 in the air and in the water, and also temperature loggers. And this is a picture of those type of buoys, box, and in front of Laguna Verde in Veracruz. And the type of result that we obtain are sketched in this figure. BOC 9 in front of Laguna Verde in Veracruz, and then operated for some time. And we deployed BOC 10 at that same location. And BOC 9, we move it to Veracruz and so on. And in this presentation, I'd like to focus more on this type of buoys, the oceanographic and marine meteorology buoy. And this is a spar buoy, ASIS buoy, they call them, the original version from Graver and Donneland. And it is not an ordinary buoy. It is rather a floating structure. The height is about 14 meters, so we roughly have 7 meters underwater and 7 meters above the water. We have a cage, which is a pentagonal prism with cylinders and a foot with a base for stabilization and a mast where the meteorological and other sensors are installed. And of course, the sensor list is more complete compared to the oceanographic, coastal oceanographic buoys. And we have a sonic anemometer, metastation, satellite modem, GPS, and we have an array of capacitance wave gauges. And we have, of course, a motion sensor, a very fine by the SVG System Incorporated. We also have a CTD with pH and oxygen sensor additionally. And we also measure CO2 in water and air. Besides, we deploy the buoys with a current meter, ADB, which is a vector from Nortek at the bottom, and also ADCP, again from Nortek, signature 1000, looking upwards. And the sketch of this type of buoys is this one. So we have this mast and cage and foot, as you can see. As I said, approximately 14 meters in length, and the cage has 5 cylinders, sketching a pentagon. In each side, we have a capacitance wave wire and one in the center. This is in order to detect the elevation of the water surface and then estimate the directional spectrum. So to give you an idea of the deployment, we deploy the buoys with a tether connected to the actual bomb by cable and floats, and it is the tether buoy which is fixed to the bottom floor. And to have an impression of the size, so you can see people working just behind the base in the yard outside our laboratories. So we deploy the bombs 1, 2, and 3. This is the time schedule of operation. At that time, we have a website for the buoys, so we can detect each data is collected. Well, not all the data collected were transmitted, but we transmitted some data every hour just to check the conditions and average variation, average variables of the environment. So we can say that at least we have some time, a few weeks of overlapping the 3 buoys. And I'd like to mention that these buoys were deployed with the help of this vessel from the Mexican Navy. So in summary, for this type of buoys, we can say that they are enhanced spar buoys in terms of instrumentation. As I said, we develop our own electronic systems and design, and it has more sensors than other buoys. I gave already the list, and the energy needed were given by batteries, rechargeable batteries. So we have a wind generator and solar panels to recharge the batteries. And the idea is, in the near future, to explore the possibility of including CO2 sensors to detect the turbulent variability of CO2 concentration in order to estimate directly the fluxes of CO2 between the ocean and the atmosphere, and also include 2 video cameras in order to have a stereo system to detect the ocean surface. So typical results are like this. This is in particular for Bomb 1 at the Perdido region in the west part of the Gulf of Mexico. And we have wind speed and in the same plot, wind direction. Here we can, this plot was from July 2018 to February 2019. And I'd like to point out a few events of high wind conditions which are very much associated with atmospheric fronts. So this is kind of an example of the results as in average the environmental conditions: air temperature and water temperature, atmospheric pressure and humidity, and heat fluxes at the surface. This is another sketch of the results, a more detailed, more focus on ocean waves. And from the wave average, we can manage to estimate the directional spectrum and then the significant wave height. And you can see that during these events of high winds of course, we also have high waves. The peak period associated and the wind speed is given in this plot. Here we can see the the frequency spectrum evolution as a function of time. So blue colors are high energy and green colors are low energy. So we can see that the spectral peak varies along the time. We would like to use synthetic aperture radars in order to understand better the conditions and trying to estimate the direction of the wave spectrum as well from the buoys and from the synthetic aperture radars. And this is a time series of the wind speed measured by BOM-1 from July 2018 to February 2019, and the significant wave height. And with the lines, we indicate the time when synthetic aperture radar images are acquired or obtained for us. And we can see that we have these events in October of high winds, one particular event in October and one particular event in November. And we also have some high winds or relatively high winds in September, and when we obtain a synthetic SAR image. This is an example of the type of SAR images that we obtain, and this is this particular one is for September the 12th, about noon, and this is the Tamaulipas State coastline. This is the BOM-1 location, and you can see kind of we could say that it is an atmospheric front. We look at the Sentinel-3 information, and what we can see is that this area is covered by clouds. Then we stress the importance of and the advantages of using SAR images when we can look at the ocean surface, even if there are cloud conditions, since the clouds are rather transparent to the microwaves. So a sub-image of that SAR image is this one, right in the position of the BOM location. And first attempt to obtain the spectrum is this as an example from the SAR image. And this is the directional wave spectrum from the BOM wave average. From the wave average at BOM, we can estimate from the at the most six channels from using the Donnellan and colleagues method to estimate the directional wave spectrum. And this is an example of directional wave spectrum that we estimate in the Gulf of Mexico. And this is rather typical. So you can see energy distributed in the frequency and direction domain. And we can see here that the wave are propagating westward or northwestward, right? We also see here the wind speed as a blue arrow, Stokes drift as a red, and the dark blue, the wind stress. And the yellow line is where the direction to the tether buoy. And this is typical, but we also have conditions where we have a complex situation on the directional wave spectrum. And this is when wind changes, and there are conditions where we have still some we could call swell, and the wind is generating waves traveling northeast. This is another example of SAR image. This is when a atmospheric front was just passing by, and this was in October the 16th, nearly midnight. And this is the location for bomb 1. We look again at Sentinel-3 information, and it is, of course, all cloudy. So with this type of sensor, we cannot see the ocean surface, but we can see it with the synthetic capture radar. And these are examples of sub-images to the sides of the front, and the directional spectrum estimated from SAR images. And from the buoy, we estimate the directional spectrum just before the front passes, and we can see that the wind here is towards the northwest, and as soon as the front passes by, and actually it's just you can see the time is 0 hours, and this is 1 hour. So 1 hour later, so we have the wind shifted, and then short waves are being generated with old waves or swell are still present. So summary and further plans. We have developed and operated enhanced spar buoys with multiple sensors in order to determine wind and wave conditions, and also determine momentum fluxes through eddy covariance method. This is of particular relevance because we have PhD students working with growth of waves in the high frequency region of the spectrum, and the conditions of complex situations with swell, and also momentum fluxes estimations for particular conditions of low wind, essentially when there are mixed seas. We tried to study the directional wave spectrum and its evolution, and the first results from SAR image to retrieve wave information under atmospheric fronts are undergoing, and spatial variability to be studied. Buoy and SAR wave spectra are rather complementary. So we can stress the importance of this type of buoys. These are kind of essential for specific CalVal studies and sites. And in the near term, we have to give some maintenance to the bombs already used in the Gulf of Mexico. And as I said, we would like to include CO2 sensors and stereo cameras. We are working with a finer version of an inversion algorithm to retrieve wave spectrum from SAR. So this is some topic that I would like to discuss with Nelson and colleagues in order to advance further. And we are still working with analysis of the data recorded and strict and very high quality control applied. Thank you very much.
Thanks, Paco. Very nice work. Now we have time for some answers.
No. We have people online.
We have.
Nice work, Paco. Congratulations to you and your large team. Have you thought to include in this interesting buoy some sensor for detect chlorophyll for algae bloom or something like this?
Not really. Will be nice, especially when dealing this time with sargasso arrivals in Mexican Caribbean regions. But so far we haven't done anything with for algae. Yeah, we can think on many other sensors, which is just additional thing, like the CO2 sensors, CO2 and cameras. CO2 sensors are of particular importance, especially if they provide the turbulent variations of CO2 concentration, like the LICOR sensors. But we still are with some struggles to deploy them in the buoy in terms of power requirements. So those sensors are really power consuming. Yeah. And the other sensors that we would like to include are a set of 2 cameras in order to obtain stereo vision of the sea surface and then detect the actual sea surface geometry.
Okay, any other question? I do have one question. Is this data you showing available on online?
It's not available online.
No.
There is some information available online, especially the transmitted every hour.
Okay.
But the transmitted every hour is just the average of wind speed, the average of significant wave height, and so on. And most of the information were recorded in hard drives in the electronics models. And these are still undergoing evaluation and processing with the help of PhD students and colleagues.
I have a question just out of curiosity. What's the cost of this buoy that you've developed, if you have it?
It costed us probably $200,000, something like that, including all instrumentations and maybe not including labor or our time.
A short question. As the Gulf of Mexico is a lot of countries involved and very important, the thing, do you share the information with other countries?
Yeah, there is a strong connection with people in the US. They do have their own consortium for research in the Gulf of Mexico, but there are links between our consortium and theirs. So we have links and strong collaboration. Yeah.
Any other question? Okay.
Did you suffer any vandalism or accident?
Very much. Yeah, well, for that particular one, the bomb one was in the west of the Gulf of Mexico, like 200 kilometers from the coastline. So at some point we received a phone call saying that the buoy was adrift, right? It was loosened and it was traveling with no destination. And they called us, and they were a fleet of vessels for servicing oil companies, doing some exploration. So I wonder if the buoy was adrift or it was put adrift. But they helped us to bring the buoy to Tampico port, and then we give it some maintenance and keep it. That's one example. But another very sad and important example is that the first buoy that we deployed, one of the small ones, the Bok 2, was deployed maybe 50 kilometers from the coast of Coatzacoalcos, the south of the Gulf of Mexico. And we deployed that one, and we went to 100 meters depth to deploy another one. We came back to port and checking internet, and the first buoy that we deployed was no longer transmitting. So next day we sent some people to check, and it was cleared. The buoy was there, the structure was there, but no sensors, no batteries. Everything disappeared in less than 48 hours. Yeah. Sorry, say again.
As probably Cesar told you, during the Delta 96 and 93 experiments at Barcelona coast near the Ebro Delta mouth, we shoot vandalism from fishermen, and we should to pay rescue for the sensors according to the MAR law, to the sea law.
Yeah, it is very difficult. It is sad, but it happens, yeah. And then what we did was to deploy in certain areas where we could have some kind of vigilance or attention from someone else. But you never know. And we have already we had some vandalism in some other buoys, or minor vandalism, and from one type or another. We are not exempt.
Thank you, Paco, again.
Thank you.
We now have the presentation of Renato Arruk from Nortek.
Você vai ter aí, ó, o tempo, mas eu vou mostrar nos 5 e 10 minutos para ir para adelante, para trás. E este é um negócio meio luminoso. É luminoso, mas é meio problema. Okay.
Good morning, everyone. I'm here speaking in the name of Nortek. My name is Renato. I'm an oceanographer. I work at Nortek Brazil. And today I've been speaking at accurate surface wave measurements from below these principles and guidance. So this is the topics that this is what I expect to achieve with you guys after this. So it's to provide a basic understanding of how subsurface wave measurements are performed, and also understand the challenges and limitations of the different techniques currently offered. As Paco explained now, vandalism is one of the big challenges we have in this field. We'll pass through Nortek's development history to show how new technologies are allowing researchers to go deeper into the studies. So as you want to go deeper, we have to go deeper into the technology to provide you the means to get what you need to do with your data. And at the end of this presentation, I hope that everyone present here should feel armed to choose the correct tool for a particular wave measurement application. So the observation requirements, waves, you guys know it more than me, that waves are random. They are not systematic and not 100% predictable. What we see on the field is like this field of waves come from different directions with different heights, with different periods. And we have to know how to decompose that to get the spectrum. So measuring waves requires sampling over a period of time that will best capture or represent the complete sea state. We can't have just one measurement and say, oh, this is the environment we have here. So we have to get it so for a long period of time to capture this moment. How long should we capture these measurements to be able to describe what's happening into the environment? As a rule of thumb, we need 100 cycles of the longest wave we would expect. So if in your region you're expecting like 10 seconds period waves, you'll have to have an equipment measuring for 1000 seconds. And by this, and when you do this, we assume that the wave field is stationary. It doesn't change. So during this 1000 seconds that you are measuring, despite of the fact that there are different waves come from different directions, the behavior is the same during all this time. So basically, the type of surface waves, the ones that ADCPs and current meters work are into this field of the wind-generated waves, which are the ones we have the highest energy. So that's why ADCPs are developed to measure in this area. And what lurks below those surface waves? As we have the winds generating waves or swell waves, it's already known that there's a signal below the surface, the orbital velocities and the pressure. The behavior is already well described in the linear wave theory. So when we have this on the surface, we generate these orbitals that goes with the wavelength. So biggest wavelength, the orbital's energy go deeper in the ocean. And if you got small frequencies, we got less energy reaching the bottom. So this is already well described, and we use this tool to collect data and then process this data. Infrared surface characteristics path to estimating wave parameters. So these are not measured directly. This is inferred from this linear theory. So we'll use this to use the parameters from non-directional parameters. And why would you want to do this? Why do we want to measure waves from below? Since we have surface buoys, you have satellites, we have other stuff. Well, Paco presented one of the first problems, fishing boats anchoring. So your measurement will be with a little trouble. Vessel traffic, if your buoy is in some location near vessel traffic, you will get some tilt during the measurement. Vandalism and theft. This is very important. At my previous job, I was working at the project that is monitoring the dam disaster that happened in Brazil 5 years ago. I've got 5 buoys. They were stolen. They were not vandalized. They disappeared with CTDs and other equipment. So it's been like $200,000 of loss for the project. We got no data from this period. So you don't have equipment. You don't have the data. So your timeline, your time series is broken in the middle. So that's another big problem that the research can't go on. So that's the principal fact that I said. And it's already an accurate method. So it's proven to be valid and to deliver good data. So that's why we suggest going under the water to do these measurements. And since I said that we are talking about history and the development of the technology, PUV method is where it all started. It measures of pressure and horizontal velocity, UNV. So as you can see here, it's a current meter, a punctual current meter. So back in the days, at the height of the equipment, we got the velocities UNV measured by the equipment and the pressure sensor. The problem with this technology is there's nothing new about it. It's been in use for almost 40 years. Nortek offers this since 2000 with these equipments. And the pressure alone provides the estimate of the non-directional parameters, height and period. And combining the pressure with the UNV measured with the equipment at the height of the equipment, you can estimate the directional spectrum. This methodology, all these measurements are inferred measurements. So there's not a measurement near the surface. So we got this linear theory, we got this UNV arriving at the equipment, and then we estimate what's happening on the surface and the pressure as well. All these methods comes with a limitation. So as I said before, depending on the wavelength of the wave, we'll get more or less energy arriving at the equipment that's on the bottom. So nothing better than a graphic to explain this better. If you want to measure the full spectrum of waves, looking at this graph here, where we get this measurement depth and the minimum wave period, we'll have to go to shallow water. In this shallow water, we'll get all the waves that are bigger than 3 seconds period. So all this range is covered with this method. And this method can also be used, and well used, if you want to, if the focus of your study are the long waves, the swell waves. So, you get like, if you install your equipment here at 15 meters, you are still able of getting the waves upper than 8.5 seconds for period. So it will depend on the objective of your study. You can work with this technology very well. But as I said, evolution, everything evolves, researcher evolves, the way you think is evolving. They developed this equipment, the AWOC, with this central transducer. And why this is so different, why this was so important? Now, these non-direction parameters, height and period, are not inferred anymore. They are directed measurements from it, since the central beam is giving a pulse to the surface and locate this surface. So we got a lot more precision of height and period. And nowadays we are working with a profiler, so the orbital velocities are captured much closer to the surface. So they are still inferred and estimated, but near the surface where the characters are pretty much similar to the surface layer. And that's how it happens. So the equipment have this AST window, which is the acoustic surface tracking. It basically will track where the surface is a long time directly. And the cell size now is getting much closer to the surface than we had in the case of the PUV, where it was just here on the bottom. And we can see in this image, it looks like it's a very big window here. But when you approach that, you can see that we have a 2 meters window, which is automatically located and configured by the equipment. And now you can have this height and height parameters in a sub-centimetric direct measurement. Like here you can see, as the bottom and as the interface between the ocean and the atmosphere, it works like a mirror. So when you got this spike, is where your surface is located. So during time, the algorithm evaluates these spikes and gives you the height direct measured. And how short can we measure? How small are the waves that we can measure with these equipments? Well, the shortest measurable wave is defined by the distance between measurements, this L here. So it's basically between the distance between the slanted beams and the central transducer. It's a geometrical limitation. The separation increases for greater depths. So shallow the water, smaller the distance between the slanted beams and the central beam. If I go deeper and deeper, this distance gets increasing. And as it's increased, it got me this limitation. So the distance between the slanted beams and the AST must be less than half of the wavelength. So if you already know the wavelength you are interested in measuring, you can estimate about you have this angle of opening from the slanted beams, and you can calculate in which depth you should install your equipment to get this data. So it is a lot better than the PUV measurement, but it still got its limitations. And nothing better than another image to show you these limitations. Now we are talking about the directional limit, which is the UNV, and the non-direction limit, AST, the height and period captured by the central beam. So in this case, if we got an equipment installed at 50 meters, we'll have waves measurement. The non-directional limit will be up from 1.4 seconds, but the directional limit has its limitation from 4.7 seconds. So you won't be able to capture waves smaller than 4.7 for the directional limits. And if I go to 100 meters, you see that the non-directional limit, we don't have too much variance here. It's 1.4 to 1.9. So it's really stable, the measurement we have from the central transducer. But when you go to this, the directional limit, the difference between, it's a lot bigger. So we solved a little bit the problem with the non-directional limits, but you still have some limitation about the directional limits depending on what is the goal of your study. And what if you want to go even deeper, above like 100 meters, if you want to install an equipment? Wave measurements from subsurface buoys. So, and you can say like, but the buoy moves a lot. You got tilt, you got it turning 360 degrees on the z-axis. So how is this compensated? So it's basically like this. We got this system of the beam coordinates, beam 1, beam 2, beam 3. After this data is collected, an algorithm transforms it to the ADCP coordinates x, y, and zeta. And after this x, y, and zeta is obtained, you match this data with the compass of the equipment, and you can pass all this to the Cartesian coordinate system, ENU. So even if it's spinning, if it is tilting, it is corrected by this algorithm. Combining U and V, measured by the slanted beams, and the AST, we have this patent technology called SUV that Nortek developed. So, as you can see here, we have this, the same case as the bottom-mounted ADCP. U and V measured near the surface, and the AST measuring the non-directional parameters directly. Deployments made easy. That's something really important for who works with deploying equipments on the field. I worked 8 years deploying equipments. I know the pain that we have to deploy with the waves are not, the sea state's not welcome, and everything is heavy when you are working. So, as you can see here, this is an employee from Nortek developing 2 equipments here, deploying 2 SIG 1000. You can see it's a small vessel, so you got less crew involved in the job, less fuel, less time, and less size of the structure that you need to use. You can deploy it in adverse conditions. There's no need to set perfectly a frame at the bottom. You can use this kick over the side method. So basically you will lose your buoy in the water and you drag it with your vessel. And when you arrive at the site, you just throw the weight and the equipment will be positioned. But how do you know that it will be vertically positioned? The floating capabilities of the buoy made that it ensures the vertical orientation of the equipment. And you can avoid the use of divers. I don't know how is this situation in other countries, but in Brazil we have a lot of trouble with this, with security. There are some divers that have to do 4 or 5 or 6 dives at the same day. And we had a lot of work relation problems with them. So if we can, we avoid using divers because of this. And what should you consider when choosing? First, the spectrum of interest. There's no need for you to have an equipment that's capable of measuring everything if your focus is just in a little part of the spectrum. So this is the first point, in my opinion, that you should look at when choosing an equipment. The depth of installation. So the depth installation will basically say, what's the equipment that you have? If you want to install at 50 meters, you have to get an equipment at least 50 meters profiling. and the type of deploy you are planning. The budget is another very important figure in any project, I believe. So if you don't have enough budget, you can go to a PUV method if the depth allow it. If the budget's not a problem, of course, go to the best equipment in the field. Energy consumption. So if you're going to deploy an equipment for more than 1 year, 2 years, you have to consider that when choosing an equipment, because it's less maintenance and less batteries and less costs for your project. And what type of data do you want to achieve it? A concurrent mode. You want to have currents and waves measured at the same time, or that's not important for your job. You can say, oh, I can have currents measuring for 2 minutes, and then when you stop measuring currents and go to waves. Or we have this. Do you need real-time transmission? That's another point when choosing an equipment. And the parameters that you want to use in your study, like the Fourier coefficients or other stuff, this also influence what you when choosing an equipment. So basically the summary, we have these 3 layers, up to 15 meters, up to 100 and 150, greater than 100 and 150. This 100 and 150 is the AWAC and the signature deployment limits. So PUV works very fine for long waves or shallow water. You got the risk of underestimating energy and short period wave events. So that graph I showed you. Up to 100 and bottom mounted AST. The orbital velocities now are measured closer to the surface, and the free surface is measured directly, and it's accurate and robust. And greater than 100 and 150, we go to a subsurface buoy, which you can throw your equipment much closer to the surface, and you don't have the problem with the geometrical limitation. Solves the limitation on the directional parameters, because you got this UNV measured close to the surface, and the AST is used for energy-based estimates of period and height. Thanks, everyone. Here we got this QR code. If anyone wants the presentation or any material regarding this, which was used to the presentation, just scan it and put your email. I'll send it back then. Thanks a lot, people.
Thank you, Renato. Very nice presentation. So we have some questions.
Thank you for the presentation. I like measurement because that's how I started my career. And I know very well your instrument because we have an oceanographic tower offshore Venice. By the way, 16-meter depths. So we have one of your instrument. So I know quite well. I would be less generous with the accuracy, of course. Of course, we have to push
Yeah, of
in
course.
your direction. We must be critical. I don't agree that twice the distance and wavelengths, actually you need much more to be accurate. One thing you didn't mention at all is wave breaking.
Is what?
Wave breaking, bubble
Oh, yes.
into the sea. That is quite a problem,
Yeah.
especially in shallow water, when you have a lot of breakers and then the bubble make a tremendous noise.
Yeah, it makes
In
a
fact,
barrier.
at that time, we shift to pressure, of course, to measure the wave height.
Yeah, no, that's a nice point. And bubbles we use, like we don't in my case, I deploy the equipments much in the deeper waters. So bubbles are just my concern when I'm at the vessel doing with ADCPs with vessels. So that's when, but mostly in the cases that I see people using, they go to vectors in these zones where we have these bubbles and waves breaking and all this type of interference that can have. I see a lot of people going to other equipments instead of these profilers because you lose range. If you got any bubble or any material in suspension, you lose length, you lose range. So you won't be able to get these measurements on the top. So that's another point that's very nice that you mentioned. So it's another thing that if you should consider when choosing an equipment. How's your environment located? So if it's in a breaking wave zone, if you got a river coming and throwing material, or these bubbles. So it's very nice to have this background.
By the way, as soon as you have a problem, you have a new market, because now there are acoustic devices to measure the noise of the bubble.
Yeah, at Nortek, we have this MIDA software that you are capable of measuring the noise floor at the environment. So for that, you have to get real-time transmission, or you have to be on site to make this test. So it's a little bit tricky, but we are moving forward to it. And it's very good to have this feedback. So when you have this, I can make it to the engineers to make them do something about it.
Thanks a lot.
Yeah.
Thanks for your presentation. And it's also nice that you are presenting in the way that you are helping researchers, so we can be critical also regarding that. My question is about the directional parameters. And the thing is that recently we were doing a study in which we were trying to get some parameters from the directional spreading and other parameters of the directional distribution. And we realized that from the buoys, actually this parameter is very inaccurate. And then that reminds me my initial times when I was starting this kind of studies in waves. The old people, they were very critical whenever you presented spectra, observed spectra, because they were always mentioning, and what's the accuracy of your spectral measurements, not without talking about the directional ones, but also about the spectrum. And somehow with time, people stopped asking that, luckily for some of us. Yeah, but actually unluckily, because I still feel that the accuracy of the wave spectrum is very limited. And somehow this topic has been erased from the talks or from the people who measure data. And I wonder how, I mean, you have very nice toys to play with that and like to evaluate by different instruments or tripod location, things like this. All these directional parameters and all the other parameters of spectrum. And I don't know if you have been doing that, or you are planning to do that, or you have somewhere in the agenda of the development some sort of these things, because I mean you have the toys to do that.
Yeah, this probably is the thing that people are doing in Norway, like Thorstein, who is the guy who developed this methodology of the AST. So basically, we probably have a lot of material and a lot of studies regarding this, but basically for the common user, that's not so. If you got this demand, we can work with you with that and go deeper. So as I said to him, so if you got a demand and our feedback is very nice, so I can bring it to them. I have some material here. I think there is something written about that. I can see that after this presentation, then I can talk with you basically on this issue.
Thank you. Very informative presentation. Quick question, I may have missed that. What's the vertical resolution? So the resolution of the wave height. And can you measure the orbital velocities inside of the crest?
It will be it depends of the equipment. But for example, for the SIG 1000, I believe is like 0.1 meters per second. I have this guide here with me with all the equipments and all the accuracy, and I can show you that again.
Okay.
It's a lot of numbers to have on my mind, yeah. A lot of equipment, but we can discuss that.
Sure. Thank you.
Thank you, Renato. Good presentation. And I think it's very important for us to understand what the sensors are doing. And especially, I agree with Jesus regarding the directionality. How do you obtain directionality, and what's the confidence? It is probably, hold on, it is probably easy, or rather easy, to determine the confidence level of the spectrum, the frequency spectrum. Just depends on the pressure and or height of the water column or so on. That's understandable. But the direction and directionality parameters are rather cumbersome. And in fact, it is important to mention that within each beam of the signature or sensor, what it is really measuring is the velocity along the beam, right? So how do you convert that along beam velocity to U and V is part of the story. And in that part of the story, you have to be very, very careful, because it is not easy to combine 4 beams very much apart, very far apart, and then say, oh, this is the U velocity of this volume of control of fluid, right? So we have to be careful on that.
Yeah, but that is what happens here, that this beam coordinates, and it's got a really massive matrix that they developed to turn it from the beam coordinates to the XYZ. And you have to have a really nice compass, calibrated compass inside your equipment, so you can be sure that these beam coordinates are really being transformed the correct way to this technology and to the Cartesian coordinate system.
Any other question? I do have a question. As a field guy, I look the news you have of the different instruments, the WAC, the signature. I wonder if you are looking to release someday a product that has several acoustic frequencies in the same instrument.
More than one frequency.
More than one frequency.
We have that on the signature 100, but just from the central beam, which is an echo sounder. It's a biomass echo sounder which can pulse from 70, 90, and 112 hertz. But that is especially because people use a lot of to study cryo biomass in Antarctic region. NOAA use it a lot. So first of all, they started with this echo sounder, but there's a lot happening that not even us know what's happening in Nortek, since there's a new here that the signature, so till today, only the AWAC was real-time transmission of calculated waves. Now we get this ability on the signature as well. So they can be, so this demand is something that people probably are already looking at Nortek, but until they have it finished, they won't release it to us, but we already have that on the echo sounder, for example.
Okay, thank you, Renato, again. Now, Juan Pablo Ramírez.
Para adelante, para atrás. El láser puede ser un poquito tricky, pero vas a tener una guía de tiempo y yo te voy a mostrar 5 días cuando te pase eso.
Okay, thank you everybody. My name is Juan Pablo Ramírez. I'm from University of Colombia, sede Medellin, and member of the research group Oceanicos. I'm going to be talking about an experiment that we carried out in Germany in order to study the turbulent motions around a coral colony and how those motions change depending on the roughness of the coral. So initially, why? Juan David and Andres already told us yesterday like the importance of studying this type of ecosystems, but especially when with coral reef, by the complexity of its geometry, turbulent processes or hydrodynamic processes can appear like in a wide range of spatial scales. And most of the studies that have been carried out is being focusing like in the reef scale and only in the geometry itself. No, but doesn't take into account like the health state of the coral and the additional roughness that the living tissue provides to the geometry of the colony. So we start to, or this study seeks to understand how the turbulent processes change according to the roughness that the coral colony had. So the experimental setup, it was made in a plume in Gießen University in Germany. So we have a coral colony of the species Stylopora piscillata, and we take velocity measurements like the velocity profile over the coral. The first point is at 9.8 centimeters from the bottom. That is just 1 millimeter from the head of the coral, and the furthest one is 10.5 centimeters, and we take measurements from 4 different flow rates or 4 different Reynolds numbers in a stationary flow, no oscillatory flow. And we take the measurements both for the coral with living tissue and without living tissue, like affecting the health state of the coral in order to understand how that additional roughness changes turbulent motions. So first of all, it's not like you don't know that it's like a proper definition of turbulence, but we have some features that are like representative of that type of motion. That is irregularity. The turbulent motions tends to be chaotic. It's highly three-dimensional. It occurs at high Reynolds numbers. It has a great capacity of diffusivity, induced mixing in flows, and is highly dissipative, taking the energy of greater scales to lesser scale, like turbulent cascade, and the energy is dissipated by heat. For this experiment, we take the turbulence fluctuation just by subtracting the mean of the flow because it's stationary. And if we have like oscillatory flow, we need to do like a high pass filter in order to remove that oscillation from the data, and only take like the deviation of each velocity from that mean, the fluctuations. So the first analysis that we carried out is about what is the most common turbulent motion that occurs above the coral in the different points that we take measurements. So quadrant analysis allows us to define 4 types of motions that each one has like a physical interpretation. So for example, the first quadrant is when I have like a particle that it goes faster than the mean flow, both in X and Z direction. So I have a particle that is faster, like downwards, but is moving upwards. So it's carrying out like an excess of energy of momentum to upper layers and is making them like go faster, the upper layers of the flow. The second quadrant that is called ejections is the opposite, when we have like a particle that is moving upwards but is slower than the layers where is getting to. So it's delaying the flow in the upper layers. The third quadrant is when we delay flow of the lower layers, a particle that is moving downwards. And the last quadrant, or the last type of motion that are sweeps, are the ones that increase the velocity of lower layers by turbulent motion. We will be focused especially in these 2 type of motion that are the ones that control like the motions that I will show you. So we have a key like I told you that we carried out this for the 4 Reynolds numbers. So we have like the lowest one and the highest one. And we have the first log is the distribution of turbulent motions for the coral with living tissue, a healthy coral, and the coral without living tissue in the last row. And we have the distribution of motions from the first point above the coral, or like the point that is more affected by the structure, and in the furthest one. So for the lowest Reynolds number, we see that those 2 motions that I mentioned, the sweeps and ejections, that generates ejection motion towards upper layers and ejections, the last quadrant, towards lower layers. control like the 62% of the total turbulent motion that we have for the coral with living tissue, and without living tissue is 55%. In the coral with living tissue, we have the motion that predominates in frequency is the one that take particles towards the coral or towards lower layers. For the coral without living tissue, we have that is the opposite one, the one that take particles and move upwards. When we increase the Reynolds number, we can see that the tendency of the turbulent motion of being aligned with that two type of motions increase. And in this case, for the coral with living tissue, we have 75% of the total turbulent motions that are represented by these two quadrants. And still, the ejections are the ones that are more frequent in the motion for almost like 10%. And for the coral without living tissue, we also increase like the tendency, but the turbulent motion that dominates that is the more frequent one change. For the coral, for the Reynolds number, it was the ejections. And for the highest Reynolds number, it changed is the sweeps, the ones toward the coral that dominates. So we start to see like a more stable behavior for the coral with living tissue, that always the sweep type of motion is the one that is the most frequent one, while for the coral without living tissue, we have like those two motions are the predominant ones, but the one that have like that occurs more or is more frequent change depending on the Reynolds condition. And like so far we have like the ejections and sweep control the transport regarding of the health state of the coral, but that his dominance of those events increase as the Reynolds number increase. But for the coral with living tissue, we have that always the sweep type of motion is the one that dominates the transport, while with the coral without living tissue, it changes depending on the Reynolds number. But just because one kind of turbulent motion occurs the most doesn't mean that is the one that carried out the more energy in the flow. So we start to analyze extreme events that with this method that we compare the Reynolds stresses generated like in one fluctuation with the average Reynolds stress of the whole series. And we define a parameter called H that defines that these hyperbolas and a region called like the whole. So if we start like with a one value of H, we are taking into account like, or a zero value, we're taking into account all the events. Sorry about that. Thank you. So we are taking into account all the events if we have a value of 0. And when we start to increase the H parameter, we generate this region, and we doesn't take into account the events that stay in that region. So we are taking into account more and more extreme events while we increase the H parameter. We can plot something like this. We compare the average Reynolds stress of one quadrant at certain value of H with the average total Reynolds stress of all the events. So we can compute like the contribution of each type of motion for the total Reynolds stress. So see like the important one, because this can tell us about how energetic the events are with respect to each other. So for this case, we have again coral with living tissue in upper row, and for the second row, coral without living tissue. For the two extreme Reynolds number, the lowest one and the highest one. And for the coral with living tissue at the lowest Reynolds number, we can see that the sweeps the ejections are the one that contribute the most for the total Reynolds stress, followed by ejection. So as we told you, in this case, even when the sweeps are the movements towards the coral are the most frequent ones, the more energetic ones are the movements that are far away from the coral, from lower layers to upper layers. This behavior is more clear for when we increase the Reynolds number. So we have that the more frequent events carry a flow towards the coral, but the more energetic ones take it out like the flow closest to the coral to upper layers. For the coral with living tissue, it's not like such difference between how energetic these type of motions are, but we can see that when we take like more and more extreme events, the ejections tend to be the more energetic ones. But again, when we increase the Reynolds number, it switch. The sweeps tends to be the more energetic one. So again, it's like more stable the behavior when the coral have like the additional roughness of the living tissue, that the most frequent event remains always the most frequent one, and the more energetic turbulent motions maintains like the more energetic one for all Reynolds number. So in summary, something that sadly I cannot show, I didn't put the graph, sorry, is that this behavior, this type of motions, when we see like the time series, we observe that this motion doesn't occur like in a random way. It's more like a cascade. We have like a group of of ejections taking place in this area, followed by a group of sweeps taking place. So it's not like a random motion, it's more like a cascade, like cascades of the same motion taking place, followed for the other event. So you have like some pattern of flow going towards the coral constantly, and then flow from the coral to upper layers. So in summary, we have like, even when the two dominant motions are the same for the two coral health states, the behavior of which is the more energetic one, or which is the more common one, change depending on the roughness of the coral. So the behavior is like more stable for the coral with living tissue. And I'm not a biologist, but we work with biologists from Germany, and they told us that the behavior that we observe for the coral with living tissue kind of have sense from a biological point of view, because it's like the coral is trying to maximize the number of motions towards him in order to catch nutrients or some other properties, but that the energy is not so high that he can catch it. And the ejections that are the more energetic ones is like taking the things that he don't need around his closer region and moving like far away. So from a biological point of view, we're working like in the mix between the biological implication with the hydrodynamic implication, but that's kind of the path that we are following. So it's like the summary, some reference, and thank you so much. I don't know if you have any questions about it.
Thanks, Juan Pablo. Very nice work. We do have some time for questions. I do have some question. Do you plan to analyze this turbulence in combination with waves?
Yeah, actually, that's my master's thesis.
Okay.
So we run some simulations in OpenFOAM, like with a less complex geometry of the submerged object, because its composition is expensive, in order to have like velocity fields with a solitary wave interacting with the object. So we are analyzing how the transport patterns change according to the geometry of the object, the relation between the height of the object and the surface height or height of the wave, or something like that. And we are doing this through Lagrangian current structures in order like to study the topology of the flow. So yeah, this was like the behavior of the
steady flow.
Yeah.
Well, yeah, thanks for interesting presentation. It's of course measurements very good. I have a question about how you separate between turbulence and waves, because there are orbital velocities of waves, and usually they are more energetic than small-scale turbulence. Or does it matter for coral? What is that, turbulence or just waves?
When we have waves, I mean, when we analyze turbulence, we need to take the turbulent fluctuations, like deviation from the mean flow, but with a wave, I have like this type of series that oscillates. So I need to have like do like a high pass filter or something like that in order to take the turbulent fluctuation. And regarding the energy, something that I need to tell is that we are not quantifying how energetic they are here, the motions, but how it's like the relation between the type of motion. So the fact that, for example, here the sweeps seems to be more energetic for the coral with living tissue than for the coral without living tissue. This is not the energy; it's the contribution of how energetic they are to the total energy of the flow. So I'm not saying that for the coral with living tissue the motions are more energetic than for the coral without living tissue. It's just like the proportion between motions.
Yeah, in your definition of turbulence at the beginning, you missed one point, because turbulence, it's vorticity should be included. And that could separate you from waves, from orbital velocities of waves. But question is for corals really important where this kind of circulation coming from really small-scale turbulence, or is it just orbital velocities of waves? Because orbital velocity of waves are always bigger than small-scale turbulence, because this source of turbulence is this orbital velocities mostly. By energy, you cannot separate it.
In this kind, I mean that for the study that we are carrying about in this moment, like all the velocity flow, when we have like the oscillatory motion, we're taking into account like all the components in order to take care only the fluctuation, and we are like proving like the turbulent fluctuation should have like a normal distribution when you plot it in order to this should be normally distributed in order to ensure that you are taking into account only a turbulent motion. That was proved here. I don't show like the histograms or the normal distribution, but the turbulence fluctuation that we measure here or that we process here follow a normal distribution, like they should be like they are requirement to be like a turbulent fluctuation.
That would be not easy to separate by just histograms. So yeah, thank you.
Okay, thank you again, Juan Pablo. We now have time for the last presentation, Carlos Herrera.
Este micrófono, este es para ir para adelante, para atrás. El láser puede ser un poquito raro, pero ahí te van a poner el tiempo.
Hi everyone, I'm Carlos Francisco Herrera Vázquez. I'm part of the WAVES group in CICESE, Mexico. This is part of my PhD work, and the collaborators is Nicolás Rasle, Francisco Campo, Pedro Zuna, y Héctor García. Okay, the title is Error Analysis in the Current Measurements by a Moving Buoy. The motivation of this work is the assays PACO. We install an acid buoy called bomb, and on this buoy we install an ADCP looking towards to measure surface currents. Okay. From this buoy, we created, from the movement of this buoy, I created these animations. This is a real movement of the buoy, and the blue points represents the free surface. Okay. from this animation, we have one question, that is, who is the error on the mean measured velocity as a consequence of the vertical and horizontal displacements of the buoy? Okay. This is the problem, and first we have an analytical approach. This is the weight bias. For a velocity field, we can apply first a Taylor expansion in order 0, 1, 2, and superior orders. And for this Taylor expansions of the velocity fields, we can apply a time average over a phase period. Okay. This is as we can calculate the stock drift, and it's very normal looking in the mathematical books, no? And okay, for orbital velocity for a monochromatic wave, I have the monochromatic wave and the orbital velocity correspond. If we have displacements of these types that is proportional to the surface displacement and decay as the velocity fluids, as the fluids paths on theta and delta x. I have these expressions. If I average, I give the stock drift. But if I only consider a displacement on the vertical and I don't have any displacements on the horizontal, I have this type of representations, and the mean velocity that I will measure is this represents on this panel. Okay. I can play with delta zeta and delta x to propose different types of movement that a buoy. In each case, the buoy is only to represent everything buoy, no? But in the first case, I only consider a buoy that whose displacements is only vertical. The case B, I only consider that the displacements on the surface that corresponds to the elevations and displacements on the horizontal are representing in all the column, and I can play and have different paths of trajectories for each case. Okay. What happens if I don't consider only orbital velocity from the linear wave theory? I can propose another type of currents. I consider for the simplest idea that I have a vertical profile that varies on the depth. For this case, if I only have a current that varies on theta, when I do an average, I have that the difference on the average currents measured will depend on the curvature that corresponds to a second derivative of the current velocity profile. This is only for a single monochromatic waves. If I want to imagine, to measure what happened with a spectral complete C state, I need to do more calculus. No? For this, we propose a simple current model where I have a fetch and wind speed, and I from this fetch and wind speed, I have a Ekman current where Ekman current was calculated using a mixing length from Craig-Banner and roughness length from Terray y colaboradores and Terray et al. 1996. From other hands, I can calculate the Young swap spectrum from Donneland et al. 1985 and use the model proposed by Donneland et al. 1992. I can reconstruct the current field from the velocity, orbital velocities. On the other hand, with the Ekman current, I repeat this Ekman current on all the time domain so that I have a mean, I have a current from waves and current from current field from waves and current field from Ekman. Using a random phase model and elevation interpolation, I can grab representations of these currents on the system that represents fixed coordinates. From this case, I have a wind speed of 4 meters and fetch of 31 kilometers. I reconstruct this current field. This is the system that follow the surface, and this is the system in fixed coordinates. This is only the case from wave orbital velocities, but a similar reconstruction I have with Ekman current. When I average these fields, I have the black line, and the red line. This is only considered an elevations as a buoy that follow only vertical, that have only vertical displacements. Okay. As we see on the animations, I have a C state, and my buoy don't follow all the waves. I consider part of the idea that the buoy acts as a filter from high frequency waves. For an idealized case, we define a cutoff frequency that represents the buoy movement responses for the wave fields. This cut frequency was represented by every line on these panels. The cut frequency corresponds to the pink color, represents a buoy that doesn't move with the waves. It's similar to fixed coordinates, to have measurements on a fixed coordinates. Cutoff on the orange region represents a buoy that move with everything, approximately everything waves in the spectrum. If I average the measurements released by a buoy that don't move with all the waves and don't move measure on fixed coordinates, I have a difference values, a different measurements that is that is the is part they are in the region that is not an Eulerian measurements and is not an surface follower measurements. Is a transitions velocity field measurements. One time that I have the current field that I can represent the movement of a buoy, I play with different fetch and difference with the speed to have different wave age systems. Different waves that have different wave age. In color, I represent the different wave age. I don't know if you can see the red color represents wave age from 1.2 and blue color represents wave age from 0.3. All these cases have been represented on these panels. First represents the Eulerian current, the Eulerian mean current calculated by all these cases. The second represents the Eulerian medition of the Ekman current. The third is the wave current considered surface following. And finally, the fourth is the Ekman current that has been considered that I have they are surface following. Okay. Only in this case, I will choose two systems, one from 1.2 wave age from this region, and another from this other region. Okay. One problem that I have is that if my buoy only responds to certain types of waves, this is a characteristic from each buoy, depends of my system. I can measure more or minus or more portions of stock drift, and this will be affected the characteristics that we have on the measurements. From this case, I propose the normalizations of the spectra. In this case, is the Stokes spectra, the waves spectra multiplied by the cube of the frequency, normalized by the own frequency, peak frequency. With this, I can say that have only three predominant comportments. That is, when the peak frequency, the movement is lower than the peak frequency, is between certain region of the peak frequency, and when the movement is much more than the peak frequency. And this is not depend from the wave age that I have in each case. And this is really interesting because depending of the characteristics of the waves, I will have the same values, and it don't depend that if they have the same cut frequency. Results, the importance of the movement of a buoy in the measurements of currents depends on the responses to the movement with respect to, from the frequency associated with the peak of the Stokes spectrum. Consider F norm equal to frequency over the peak frequency of a Stokes spectrum. I consider that if the movement of the buoy responds from lower than the F norm lower than 1, this meditions tends to Eulerian mean. If F norm corresponds from 1 to 2, I have in a transition region. If the F norm corresponds to is greater than 2, tends to a surface following mean. Finally, the difference in the measurements framework occurs but mainly in the confined region between significant wave height. Also, the measurements of the currents by a moving buoy is related to the characteristics of the movement. The error will be proportional to the Stokes drift, and its magnitude and characteristics are determined by the variables analyzed on this work. And thanks.
Thanks, Juan Carlos Francisco. Very nice work. We do have some questions.
Carlos, that was very nice work. What I was wondering, though, is you're basing this on the response of the buoy in the ocean, and you're working with Paco's buoys. Now, I'm assuming the buoys last long enough and they're not borrowed by fishermen. But what I'd like to know is, can you say anything about the change in the response of the buoy from biofouling over long deployments? Do the buoys slow down, or any response in the tilting from heavy growth in the under portions of the buoy, the submerged parts?
I only consider the movement of the buoy from that moves different from the surface, but it's only that the buoy don't follow all the surface. The center of mass of the buoy in a repose, in a quiet, this is the thing that I calculate, only this.
Okay. I'm curious about that because, back when I was a grad student, I used to do a lot of work with submerged buoys, and after 6 months, you have quite a bit of mass built up in the lower sections of the buoys, and my job was to clean that. No fun. But that would change your response, and as you mentioned, these buoys, movement in the water acts as a low-pass filter, and the heavier the buildup, the increased drag on it, the more that will change your equations.
I only consider the cut frequency. If the buoy is so big, the cut frequency was on the lower frequencies.
Yes, that's true.
I don't consider the size. I only consider the cut frequency. And it represents from one case, I have several cut frequencies, and represents difference. One cut frequency represents one type of buoy.
Okay.
From A1, I have 50. No?
Thank you.
Any other question? I do have a question. Of course, it depends on also in the mooring you have of the buoy. Do you plan to do some work in laboratory in order to validate this model?
No, but the first part of my work was how do you say, all the mediation released with the buoy, and this is that I can apply, but we don't consider laboratory experiments.
Okay. So thank you again. We do have time for coffee and the next session.
Good morning again. Thank you very much. This is the 6th session of LatWaves entitled Marine Energy, and the first speaker is Rodrigo Alonso from Uruguay. He is presenting wave energy studies in Uruguay.
Thank you, Walter. Hi, everybody. Okay, this presentation. This presentation don't pretend to be a keynote, only present to you some of the main results that were obtained in this research topic, started by the Professor Luis Teixeira in the 2010, and after this date, there are some interesting works that we done in collaboration with this team. So I need the So basically, we worked in two topics. One is wave climatology analysis in order to characterize, to assess the wave energy resource, and the other is some work in a device, in a particular device. As you know, wave energy converters are the different types of wave energy converters. They work with different ideas, with different mechanisms. So in order to, the idea was not to develop a device. The idea was learn how to study devices, how to study with numerical models, or how to study with physical models. So we choose one of them, the ones called oscillating wave surge converter. This is a flap that oscillates with an horizontal axis in the bottom and force a hydraulical cylinder. So, okay, I'm going to present some results in these two topics. So related to the wave resource assessment, they are based on wave hindcast, local wave hindcast that we developed for Uruguay. We performed two wave hindcasts. This is the last one that is published in Coastal Engineering. An overview of the configuration of the grids. We use the WaveWatch3 model in a multi-grid mode. There is a two-way nesting between 5 grids. The coarser one is a global grid in order to don't use boundary conditions. All the waves are generated in the model. Then a grid for the South Atlantic, then a regional grid, and these are the high-resolution grids for the intermediate and inner Rio de la Plata, and also for the outer Rio de la Plata and the Atlantic coast and the continental shelf. So in this, the forcing, the wind input was the CFSR winds, and we use also, there is important, as you know, the Rio de la Plata is shallow, so there is important the water level variations due to meteorological forcings change the water depth along the waves propagate. So it is important to consider these variations of water level. So we use non-stationary water levels and currents, also current, provided by a hindcast of water levels and current using the Telemac model. So these are the results in terms of significant wave height for 4 different regions. the intermediate and inner Rio de la Plata, the outer Rio de la Plata, and 2 regions in the Atlantic. So in the Atlantic, the performance of the hindcats is well. In the Rio de la Plata also, but there is most scarce of the data. And also, I know some that Luigi told yesterday about this. This is an overestimation of significant wave height, that it could be due to that the bottom here, the bottom is a mud bottom, that for lower waves, moderate waves, it is like a smooth surface, a consolidated smooth surface. Bottom friction is lower than a typical sand bottom, but for higher waves, probably trigger a fluidification of the bottom and trigger a process of wave damping that is not considered in the model. So we are probably overestimating wave energy in this part of the estuary. But thinking in wave energy, here the wave energy is very low. No? The swells are dissipated by bottom friction when they enter in the estuary. So the most attractive in terms of wave energy is the Atlantic coast. This is the map of the resource in terms of average omnidirectional wave power. At the edge of the continental shelf, we have 30 kilowatts per meter, then decrease, and we have 10 kilowatt per meters, very close to the shore, maybe at 10 meters height. So that's the map. I'm going to present some interesting results that we proposed in order to assess a wave energy resource. One is this index. It's called ether exploitation to extreme radio. The idea is to compare this wave height. That is the wave height that this is a diagram with periods and wave heights, and the mean annual energy that is that correspond to each of these bins correspond to some sea states. So this wave height is the correspond to the sea states that provide more energy. So, and it is compared with the wave height for the structural design of the wake in order to guarantee its survivability. So this wave height is obtained for an extreme analysis, considering a return period reasonably to design this kind of structures. So we can think in this index as a structural efficiency of the design of this kind of wake. So another analysis that we propose is to the assessment of when energy that's composed in terms of wave energy systems. So we identified 4 wave systems. One's wind seas, and there are 2 systems of swells. One associated, one that we call it southern swells that come from the south, and the others that come from the east. But due to refraction, when in the Rio de la Plata, they join together, and we can't distinguish one from the other. So we call it them Rio de la Plata swells. So one question is what is the generation area of these swells? to do that, we use this method proposed by Shen and Mu. The idea is to correlate the wave height of the swells with the wind velocity projected on the great circles. Here there are the great circles that connect all the oceans of the world with our study sun without the interruption of land. So this is all the potential area that swells can be generated. So we correlate significant wave height of the swells with the velocity of the wind projected in these great circles, and considering a time lag. So we consider a time lag and keep with the maximum correlation. So this is the map for the southern swells. They delimit the zone where they are generated, and this is the map for the eastern swells. So these diagrams shows the energy fluxes, wave energy fluxes along the coast. This point correspond to this one, and advance in this to the westward in this direction. The red arrow correspond to the southern swells. Yellow arrow correspond to the eastern swells, and the blue one is the wind seas. So in the Atlantic, we have this pattern, and then these two swells in the Rio de la Plata, we can distinguish one from the other. There is a green arrow, and then domain the wind seas. Another interesting results correspond to one of the characteristic of this resource is it has a lower interannual variability, but it's in this variability we try to correlate with some climate indexes. So we performed some correlations between the monthly average energy of the spectrum with different climate indexes. We find some correlations with the Antarctic oscillation, a positive correlation for this part of the spectrum that correspond to the eastern swells, and a negative correlation with this part of the spectrum that correspond to the southern swells. And only in this part of the spectrum we find some lower but statistical significant correlation with the southern oscillation. Okay, in terms of this result were published in different papers. You have there if you want to look for more details. So I go to the other work, the study on the web device. So we started with some analytical approaches, linear waves, also linear power takeoff, and thinking in a 2D problem. Then we go to the laboratory, and this guy Moisés Brito. Most of the results that I'm going to present now were done by Moisés. He did his PhD thesis in Portugal, and he were here working in our laboratory. He did his experiment with us in our laboratory. So this is the laboratory. Here is the wave flume. the dimensions. This is the scale of the flap. I'm going to say flap to the oscillating wave surge converter. This is a physical model 1 to 10, the scale 1 to 10. So our instruments to measure waves, we have capacitance sensors. We have different sensors to measure velocity, to measure pressure, to measure the motion of the flap. So what are the results obtained with these experiments? The first is that the problem is the nonlinear effects are significant. These are red curves are the result that we obtain in our analytical models. Consider the hypothesis of linearity. This is the result of the experiment. This is a measure of the performance of the device. Moises worked with CFD, Lagrangian model, the HPH, coupled with another model that model the movement, the dynamic of the flap. No, the dual physics was coupled with the chrono. So they modeled the waves device interaction. So his results are in a good agreement with the experimental data. These are we can consider this. Sorry for that. Here I present a comparison between the experimental data and the results obtained with this couple SF-physics, Lagrangian, CFD fluid mechanics models and Chronos that model the dynamics of the flap coupled with the hydraulic cylinder. So, the model is validated. So the other step is to optimize the device in order to increase its performance. So they change some parameters of the hydraulic cylinder. He changed some parameters of the inertia of the flap, and they quantify the change that we can obtain with this improvement in the design. Also the geometry. There are changes in the performance associated with the geometry of the device. So work in progress. Now we are taking these results of Moises and improved our flap. This is the wave flume, and I don't know if it is the next talk of maybe one of the talk of this session is going to be by Alejandro Haim, a colleague from Argentina. They developed this WEC, and now we are testing it in our wave flume. So I have an invitation that is at the end of the last session of this day, and after that, and before the dinner, for those who are interested to visit the flume, we can organize to go there. So the idea is to go when we after we finish and before the dinner. Okay, that's all.
Thank you very much, Rodrigo. Any question? Luigi?
Thank you, Rodrigo, for talking practical problem between the balance between theory and practical applicability. And my question to you is a very interesting study. Is there a real plan in different extract energy? I'm asking this point because I'm not aware of any place in the world, where they manage to put a real system at work. Because there was a paper which came some years ago, and the problem that, especially in the second device of the system, is very less. And however, can you imagine that it's starting to repeat? Because you have to extract energy from over 1 meter, this is a great part. But then you have to send changes. And that's the problem.
That's
Sorry. It was not on, sorry. No, okay, you can.
No, but sorry for interrupt you, Luigi. But
please go ahead.
that's the idea of this index. It's to compare the wave height that you have to harness the energy, and the wave height that you have to
withstand.
To withstand. That's the word. So our wave climate, it's a little bit moderate in terms of mean wave energy, but is the extreme events are relatively benign. So this index, the values we have a better index than other places of the world.
Yeah, but to give you an idea of the problem, the question we asked with Jesus was if it was worthwhile to put wave energy converter either at the Galapagos Island on the Ecuador or to the Azores, where you can have 10, 15 meters significant wave height. It turned out that the right place is Ecuador, because you have a permanent swell of 1 or 2 meters without extremes. So the cost of the structure is up to that. On the contrary, if you go to Azores, you have to rely on the 2-3 meter swell, usually. That is your budget, positive budget, but your structure must withstand 15 meter significant wave height, which makes the problem absolutely unpractical. And that's why, whenever you put a moving system into the sea, maintenance costs are awful. That's a problem, you know.
Yeah.
Thank you for the interesting talk, and I'm glad to see that there is some interest again in the oscillating wave surge converter. Because 10 years ago, I had a 5-year project on this with the Oyster device, with Aquamarine Power. And so to answer Luigi, so it worked. You know, there was a prototype in the yes, well, at EMAG and it produced electricity, and so at least, you know, the concept works. But then, you know, the company had to stop because of no more money, you know, so the investors stopped supporting the project. So it is really tough. And also, you know, we did a lot of studies, analytical, experimental, and also, you know, the measurements at sea and so on. So we worked a lot on this, and you know, it works, but there are so many difficulties, you know, with this type of devices that I'm not sure that it's a realistic device.
Thank you, Fred. And also replying to Luigi, right? That I know this kind of devices installed at sea, right? Australia has had a experience with that, right? One of our previous governments funded 5 different companies, right, to develop a full-scale prototype and install them at sea, right? And you would be surprised the solutions people come with, right? Obviously, there is this problem, right? How you withstand the extreme waves, and they solve that, right? Out of 5 devices, one when they were transporting that to the place of installation sank, right? So that was our 2. I'm not aware what happened to them, but another 2 were actually installed, and they provide energy into the grid. So it's successful installation, except it is very expensive, right? So you're prepared to pay 3 times more. It's there, right? And it's producing electricity and provides energy into the local grid. In Australia, it makes sense because some communities are very remote, right? So it's cheaper to have it there, rather than, you know, put the power lines.
Thank you, Rodrigo, for your presentation. And yeah, of course, you open up a nice discussion. I'd like to mention that it is really important to go to new designs. So that's why it is interesting to talk to people, young people that might have new ideas for wave energy converters, right? Because as Luigi said, Luigi and us have the solution. We don't need to build a big structure because it costs a lot, and we don't need energy in the in the Azores because the waves are too high, right? But there are places in the world, and especially in our countries, where we need energy at moderate scale, and then we have waves at moderate scale. So they are swell kind of permanent without many extremes, really extremes. So we need to design devices proper for the wave climate in our regions. Doesn't matter if it is not high waves as in high latitudes, that's fine. But they could provide energy at a moderate scale in remote places. We have in Mexico many coastal regions where there is no connection to the national grid. So small devices or a small group of devices could provide energy to communities, to populations, to fisheries camps or things like that. So, but I would like to stress the point that we need new ideas, new designs, right?
Okay. I agree with you, Paco. Only a comment. The flap, this type of device, it's a good idea to withstand storm loads, because if you forecast the storm, the device can be turned down over the bottom. So there are some strategies to survive. Yeah. It's not my idea. Next step. Okay. Unfortunately, all of these results was founded by a fund for research in energy that we haven't had more access to this fund, but we connect with people in the world. So this what I show you in the last slide. Now we are we are collaborating with an international project with funds from Eranet LAC. They want to link European centers with Latin American centers, and there is a project that we participate with the tools that we developed to assess the results, and also the wave flume is one of the facilities of the project. Paco also participates in this project. This project is coordinated by the Mexican colleagues. Okay, and the other, we are integrating an academical network. It's called REMAR. That this it has a Spanish coordinator. That this is a program of academical networks that want to links Latin America with Iberoamerica, Spain and Portugal. All of the participants of this session, we are members of this network. So actually, our current activity is this kind of international collaboration. Maybe now in Uruguay, they are talking about green hydrogen. Maybe this could be a window that is opened for this kind of technology, and maybe we can get fund from, but I don't know.
Well, thank you very much again, Rodrigo. The next speaker is Alejandro Haim from Argentina, and the title of his work is Wave Energy, Argentina, Technology for Generation of Electric Power.
Hello, my name is Alexander Haim. I don't have enough time to prepare an English presentation, so the presentation is going to be in Spanish. Sorry for that. And I'm going to speak in English and some things in Spanish, okay? Well, I am a mechanical engineer from Argentina, UTM University, and I am the director of this project that something told you, Rodrigo. This is our idea that generate electricity from the waves. These buoys capture the electricity and move a mechanism that move an electric generator. This is an animation. I don't know if you, Paula, could put play in this video. Okay, but this boy make a vertical move, and this active a mechanism that this mechanism move an electric generator. The principal mechanism is here inside. We have a technical problem. Okay. Well, next. No, I have my computer there. If you want to change the computer. I have several videos, so PDF is not the solution, I think. I have a password. Paula? ¿Presentación? ¿Abrir la presentación? Paula, ¿sigas pasando la presentación?
Igual si me voy a bajar.
Ah.
Por ahora, intentemos así, pero ahora está. Mientras probamos entonces, si querés continuar así,
Okay.
pero...
Bueno, ¿este es PDF o el...?
No, este es PowerPoint.
Ah, bueno.
Pero me tira de...
Ah, okay. Let's go. Well, this is the idea. This device could be installed by different form, with a platform or with a column. So we have worked about more than 10 years with the project with different steps. We made choose scale 120 and 1:10, and now we are working in 1:1 scale. We have present patents, 3 patents about this technology in Argentina, and this is the dates of the patent has been presented, and this is the first that was approved. Okay, the government allow the government in 250 allow this project, and sería lo declaró de interés nacional, no sé cómo se diría en castellano. Si Walter tenés el micrófono, ¿eh?
It was declared as the national interest.
Okay, thanks. And in the last year, the government congratulations for our works. We participate in another project with the IADO and the graphic. Walter is the director of the Wave Energy Department. That the group is going to install 5 buoys in the Buenos Aires coast to para ver medir observarle, to know the swell or the wave energy in this cost. We presented in the FONARSEC convocatory that this give 50 millions of Argentine pesos, is about $500 dollars. And we participate with Rodrigo in the REMAR network and the REMAR network. If you want to participate, the Uruguay people have to talk about Rodrigo and the people from Argentina with me. This is a wave energy network for researchers. And this is the country. This is here is Uruguay in the bottom. And then there are a student network that if the students that are here in the room, if you want to participate, we have to talk with Rodrigo too. He's the embajador sería, from Uruguay. I am from Argentina. Well, we tested this prototype 1 to 10 in Argentina with good results. This is a video how it's work with 10 centimeters high of about the waves, no? And 1 second from a period of 1 second. In the video, you can see the lights that shining here. That the white electric generator is a transformation here. This is a second video how it's work. Now yesterday we test this prototype here in the Rodrigo's channel that he invited about 6 p.m. to this channel today. If you want to look the channel and the prototype working. We drink mate. And this is the video. The video de Rodrigo shows.
30 centímetros, periodo 2,2 segundos.
Here in the... Vamos para adelante. Sorry. A ver si... Here is the lights shining. Well, if you want to know how electricity could generate this project, for example, 200 buoys have a potential about 6 megawatts, and it's equal to 500 homes or 20,000 people. The environmental impact is very low about this technology. For example, the visual impact compared with generator wind is too low. Only 5 meters over the sea, and this have more of 100 meters high. This is a simulator to prove the next step in a platform in Buenos Aires coast. This is the mechanism. We don't use hydraulic system, only mechanical system to transform the wave energy into electricity. We are going to put this prototype in real scale in Mar del Plata, in the Mar del Plata port, in this place. So this is our dream. Thanks. Any question? Do you understand me? Levante la mano si me entendieron.
First in English and later in Spanish. Did you use this in Buenos Aires or in Mar del Plata? ¿Esto lo están usando en Buenos Aires o en Mar del Plata?
We are the research group is located in Buenos Aires, but we are thinking to put this device in Mar del Plata because the energy of Buenos Aires is too low. Thanks.
You talked about two projects, one from Pampa Azul and the other one from our SEC project. Are they two different ones or the same one?
No, it's different. The Pampa Azul project is about buoys that measure the waves, okay? And the FONARSEC project is for
the prototype.
For made this prototype and put in the port. Alexander.
Thank you, Alejandro. About the feasibility, right? Rodrigo presented the investigation of the energy in Uruguay, but it's very close to Argentina, right? So there's plenty of wave energy, obviously, on average. But it also depends on how many storm days you have, right? Or you're going to use swell. It's like, will this device be able to produce energy every day? Or if not, how many days per year?
Yes, the device is designed to support storm for about 5 meters tall. I am talking about the waves, and the higher waves in this locality is about 4 meters. There are ahistoric waves about 6 meters. So the design was made to work all the time, okay? And the minimal waves is about 0.5 meters. And then up about this measure, the device start to generate. Okay,
So how many days above this minimum of 0.45 meters you have per year?
You are talking about the capacity factor?
No. How many days per year it will be operational? So you will have waves above 0.45 meters.
In this locator, this locator is an strategic located because it was protected from the storm. Because there are another ¿Collera cómo sería, Walter? ¿Cómo? There are another breakwater in the sea, so we don't know exactly how many times it's going to work because we don't put the prototype there. So I think that is going to work I don't know exactly to say a number, but it's strategic located for test the prototype. So the final idea is to put the prototype offshore. So the capacity factor in this place is very, very high, about 50%. So the 50% of the time is working to nominal potential. Okay, I answer very well. Question? Okay. Another question?
Hi, hello. It's nice to see your report. I think that it's a very interesting project, and I would like to know more about the days. How many days in the year this prototype or instrument will be working? As my colleague said already, it's very important to know this. If you don't know already, it's very important that you work on it, because if this project doesn't work every day, its cost will rise every day. So I suggest that you perform an assessment of the potential availability, considering long terms of climate events such as climate variability oscillations, because maybe in 10 years later, 30 years later, the wave energy won't be the same. So the project will fall. And this is just a suggestion. If you're doing that, congratulations. But non-projects in the past years have failed because this issue, they don't know what's going on in the future, and the cost will increase. The doubts are around between the investors. Yeah.
Yeah. I understand that you say we don't have this information in this place because in Argentina don't have enough buoys to measure the waves. So we only have simulated with wave watch stress and SWAM, but we don't have buoys working in the sea, and we don't know exactly what energy have in the sea. So it's difficult. We know how electricity produce the prototype, but we don't know exactly the waves, the energy waves in this place. So this information is part of the project. Offshore of the coast, we know exactly how it's going to produce. That is this information that I show here. Okay.
Thank you.
A comment about your last reply is that offshore, the information about wave energy is amply available, of course. You can have ERA 5 the last 70 years of this sort of things, And of course, there are simple methods to derive what happened to the coast. But my question was different in any case. The cost of energy in Europe at the moment is of the order of 30-40 cents of dollar per kilowatt hour. Of course, due to the present situation and what happens in the future or whatever, this cost is going to rise. There is no doubt. Which is your estimate of the cost of this production? Not only installation, but maintenance. Because maintenance is a basic problem of a device, a working and moving device into the sea environment.
Yeah, we estimate that the cost to put this technology offshore is about $1 million per megawatt. This is the installation cost, and we estimate that the cost of the electricity will be about $200 per kilowatt. Se me fue en las unidades.
$200 per kilowatt hour? No.
No, per megawatt hour. Ahora estoy mezclando las unidades, pero el costo está bien, ¿no? Por megawatt. $200 per megawatt hour. This is the cost of the estimate of the cost of the electricity.
Seems to me a bit optimistic, honestly. It's very easy to underestimate the cost, especially the maintenance cost. Anyhow,
no,
good luck.
We are going to know the exactly number when we test the technology in the sea. It's the next step.
I have just some comments. First, I see that there is a large number of structures at sea. I will say that installing them will be quite challenging because, you know, the installation costs are about 30% of the total costs. So, and it doesn't include maintenance. We have a lot of mechanical, electrical devices inside. So going and access them and trying to replace them will be quite challenging. Say if you have a generator there, it will be very difficult to replace it. On the other hand, we have talked a little bit about extremes that can occur, and you need to design structures for those extremes. But you also have the problem of fatigue. So there will be mechanical parts, and mostly in these devices, fatigue is a big issue because you want to get in resonance with the waves. And when you get in resonance, you have very large forces, stresses, and this is a big issue as well. The commissioning is another problem because you have a lot of devices. How are you going to remove them at the end of the life cycle? So these are things that we need to think about in the phase of developing new concepts because they will be a big issue later on and will represent a large cost within the project. Thank you.
Yeah, and the question, what is the question? Okay. Thanks.
Alex?
Just a small comment because there were questions about estimation of the wave energy. Alejandro, we did the 70-year hindcast globally, including the Argentinian cost, of course, right? So these data are open source available, can be accessed, right? So that would show the wave energy over 70 years, right, in any location globally.
Me perdí el final. Walter, si me puedes traducir.
Modelado de 70 años de olas en el mundo que se pueden aprovechar.
Que está disponible.
Claro.
Okay, thanks. To the people who ask about the cost of electricity, this is only a part about this project. We have to see about the matrix, the electricity matrix. In Argentina is only the main part is with fossil fuels, and we must to change it. So here in Uruguay, the matrix is renewable principle, no? In Argentina, no. So we had to change it, and the photovoltaics panels and the wind turbines in Argentina come from another country. It's not our technology. So this is our technology. This is another thing that we have to develop with to give work to the people and and create the technology for our country. So this is not only the price of the electricity, so this have another advantages. We talk with INVAP. We have a meeting about 6 months ago with the project, but they say that this project is a little green. So we are going to in Argentina this project with sería a largo plazo, ¿no? No son rentables por el cambio sistemático que tenemos en Argentina, donde las políticas no se sostienen. Entonces, las empresas apuestan a proyectos más a corto plazo.
I fully agree with you. It's not a technical problem. It's a socio-economical political problem. But Pescarmone Group, IMSA, moves to Brazil its production on wind generators, not for technical reasons.
Sí, con INVAP tuvimos charlas, con Pescarmona no. Sería interesante por ahí que le llegue la información del proyecto. Gracias.
Thank you very much, Alejandro.
I have another question. Alejandro, that's a very interesting discussion about efficiency of wave energy. There is another way to extract energy from the ocean. It's ocean currents with turbines. What do you think on global scale would be wave extraction will be it more effective or less effective on global scale compared to that energy of currents, ocean currents?
Walter, ¿me traducís qué me...
Preocupado por las corrientes.
The current. No, it's not is a problem for the device, the current?
No, these devices, of course, are not for extraction of energy of currents, but there is another approach when people are trying to get energy of currents transformed into electricity. What would you compare? How effective, cost effective are these two approaches?
The cost of the current electricity is I don't know exactly the number, but this is a new technology. So this thing, the people who work in this technology in another country don't say how it's cost because they are testing this device. So this information is not public. For example, no. In this case, we can use the structure to put wave energy over the sea, and under the water put current energy, for example, no? And you use the same structure to lower the cost of this technology. So there are so many variants about this technology and the current technology that the cost is it could be different because the context of the oceanography characteristics, no? Okay. I don't know if I answered your question.
Kind of. I'll talk to you after the session.
Okay.
Thank you.
Thanks.
Thank you very much, Alejandro.
Hello, everyone. I'm Juan. I'm professor from the Universidad del Valle in Colombia, which is located in Cali City. It's the second city related to population. And today I'm going to talk about some results that I tried to present 2 years ago, but the pandemic that doesn't allow me. So these are some results, and I will show you some results that are undergoing. Okay, this is the first question. Why marine energy is in Colombia? So we have Gracias. Okay, so we have the Caribbean Sea in the north and the Pacific Ocean. So in this area, we have tides with mesoscale, semi-diurnal, and I might say that this kind of tides in South America are not common. So this is a chance for extracting tidal power. These are some results that some colleagues published several years ago, recently papers. So we can see ocean thermal, offshore wind, salinity gradient, and wind and waves power. So the tidal power in Colombia is unknown already. Maybe some papers, but I'll tell you later why I'm saying that. In this picture, you can see a tree with several options for extracting renewable energy. So in Colombia, we have wind, hydro, biomass, marine, geothermal, and solar, of course. So what's going on with tidal power? Okay, let me tell you, let me show you three samples of the main technologies in tidal power. The first one is tidal barrages. It's the same as a dam in the continental areas. Hydroelectrics, as you might know in several cities. Tidal barrages is the same as a hydroelectrical dam. So they are installed nearby the coast. Tidal fences are vertical axial turbines, and tidal turbines are horizontal axial turbines. So we have three main options, and we are researching which option might be the best for Colombia. So previous studies, there are two research articles related to tidal energy, but this is the first one article with an engineering approach telling us information of the power availability in specific areas in the middle area of the Colombian Pacific Ocean. So you might find this article in ResearchGate. It's open access. So I'm going to show you this result of this paper because it's related to this speech. So what did we do? The study area is located here, nearby Cali City. So we set 4 monitoring points to understand the tidal power variability. These are the methods that we apply. So we perform a data management, then we applied a numerical method. Its name is Delft 3D model. After that, we revise the data and we calculated the available power of tide. After that, we identified how many houses might be energized. So this is this magenta line are the boundaries of the hydrodynamic model. So in this area, we implement this approach. So here in the middle, this is the Delft 3D flow, and it's double couple integrated with SWAN online. So the simulation is online. So Delft 3D solves the hydrodynamics, provide currents to SWAN, and SWAN provides wave stress and other wave parameters to the hydrodynamic model. The models were fed with NAR information, atmospheric data, temperature and salinity from World Ocean Atlas. We use the Grenoble model for providing tidal time series. We use topo nautical charts of Colombia for bathymetry and them. And we use the WW3 wave data for the wave model. So we solve and we got water levels and waves. These are results of the mentioned paper that I told you recently. But what we find here is that this is the in situ tidal station. So we compare this information against the numerical results. And we found that in the highest amplitudes, there were differences between the in situ and the model data. At that moment, the research was performed with scarce data, so it was difficult to understand why this difference among the measure and the modeled. But despite that, the model underestimated the tidal heights, that was not a problem because we consider it as a security factor. So we are working or we are calculating tidal power with lower values that might be. So we go ahead, we check the tidal harmonics. These are some results of the hydrodynamic fields. So these labels A, B, C, D are the 4 stations that I showed you earlier. These stations. So we check the velocity currents in the area. We check water levels. And these results might be considered not interesting for other researchers because tidal power is considered feasible within or about 5 meters of water level ranges. But we consider that tidal power not only can be extracted from velocity currents, we can use the hydraulic head, so maybe integrating hydraulic structures such as the tidal barrages, maybe we could extract tidal power with heights, hydraulic heads, and velocity currents. Also, despite these velocity currents might not be higher than other places around the world, we could use micro hydrokinetic turbines. So we can set several micro turbines in a field, and we could extract energy with small technologies. So we calculated the tidal power using the velocity currents, and here you can see the energy, accumulated energy consumption of houses located in Buenaventura city, which is a city in this place of the map. This is the city, Buenaventura city. So we check how many houses could be access to this tidal power. So we perform calculations using a swept area of 2 meters, and here are some results. We verify the periods or time periods where the power production is not available. These are some power results. And what are we doing now? So we are using a similar scheme of numerical modeling, but we are using now ERA 5 for atmospheric and wave data, water level of ERA 5, and we are validating and calibrating with other in situ information of waves and water levels. And these are some results for 1 year of measured data against model data. You might see these results. They are very good compared to the previous results. And we are using a multi-domain hydrodynamic numerical modeling. And this is a previous research paper where you can find the setup files of the 3D model. And multi-domain modeling its difference compared to nested models. Nested model is that we optimize the time. We don't need to recalculate the interest, in a specific area. So we reduce the computational time. And what we're going to do, we hope to show these results in the next LatWaves, is to validate multi-domain model, the previous model I showed you, with ADCP current profiles, 5 minutes time interval of 2021 year, waves, water levels. We want to evaluate the effect of change in bathymetry, structures, and climate change over kinetic and potential tidal energy. We want to explain nonlinear interactions among tides, current, wind waves. We want to identify the proper tidal technologies. And we want to increase the TRE levels through new models and new prototypes. Thank you. These are some pics of my city. Thank you.
Questions? I have one. I'm sorry.
Could you explain again the last part of the nesting models? I didn't get that. Yeah. What are you doing here? Yeah.
Okay. And you can find more details in this research paper, which is related to a research article published in 2019. Basically, you have this mesh grid. So you cut this area and integrate a finer grid, yeah, with more resolution. So I label this mesh grid as father grid with 1 kilometer of resolution, and the sun grid in the inner side is 10 plus 10 meters of resolution. so you can reduce the computational time. And in the previous research article, we checked the results, and the transitions among the grids were good. So this is a nice approach to perform numerical simulations.
Any question? Where is the most convenient zone to exploit the tidal energy in Colombia?
Good question. I'm going to show you. I started to research tidal energy 1 year ago, because I was working with offshore wind energy. So I moved to the Pacific Ocean because tides are interesting for me. And I might say that at the moment, I might tell you that bed places are within these coastal areas, but we are checking if micro hydroconnected turbines could be placed in these regions, or maybe hydraulic structures, concrete structures like dams. We are performing research. This is the Pacific Ocean, and this is the coastal area. So all these regions shows semi-diurnal and with mesoscale regime tides. So maybe all this area could be feasible to producing tidal power.
Any question more? Thank you very much again.
Thank you.
The next speaker is Emiliano Gorr, and the work is entitled Marine Ecopark Driven by Wave Energy Techno-Economic Feasibility in Baja California.
Good afternoon, ladies and gentlemen. First of all, thank you very much for the invitation in the fourth LatWaves. It's an honor to be here with you. I'm gonna to present the entitled Marine Ecoparks Driven by Wave Energy Techno-Economic Feasibility in Baja California, with the participation of Dr. Garcia Nava and Sartuche González from Autonomous University of Baja California, Ms. Garcia Vega from UNAM, Mexico City, and Mr. Larrañaga from University of Toulouse. So I'm gonna start quickly define marine renewable energy, or MRE. When I say this, I mean all forms of energy derived directly from seas and oceans. And there are five main different sources, like ocean current and tidal, ocean waves, thermal and salinity gradient, and offshore wind production. Particularly, harnessing wave energy has become a promoter of marine renewable ocean that can produce significant benefits in reducing coastal vulnerability and mitigating climate change. Some potential advantages are related with the high energy density per unit area, predictable flow naturally from generation zones to the coast, where can be harnessing by wave energy converters or WECs, and in the last decade have significant progress in the technological readiness level and for its future energy supply, but also still face potential challenge related with the resource availability and intermittency that produce, for of course, conditions, the capacity factor, its annual energy production, and its levelized cost of energy. Well, uncertainties, we talk about this, associated with a large and diverse portfolio of prototypes, and needs for, of course, uncertainty associated with its performance in the commercial performance scale. Plus, like the energy policy sensitive, it directly condition impacts the financial and commercial limitations. So we need a paradigm shift to improve its commercialization, and this is why recently marine renewable industry is been looking for new opportunities, markets, and it's why today we wanna focus in marine ecoparks, or MEP. When I say this, I mean or defining like a multiple purpose collocated systems that could offer a sustainable option to accelerate the viability of the pre-commercial marine renewable stage and powering the blue economy. Between the difference amount of different options that we can integrate in these systems, particularly marine aquaculture and seawater desalination, appear to be a viable symbiotic integration to these different wave energy converters plants, and some different potential advantage are related in the case of marine aquaculture, like this had the highest growth food production system in the last decade, add resilience to the global system food, and is expected to continue to improve the performance, economic performance in the next future. But it also potential challenge related with the development in isolated areas without electricity, like Baja California. I'm gonna present now this topic, and the lack of investor and search of new investor for economy scale, and search of a new market opportunity like marine renewable options. So on the other hand, seaweed desalination is a promising option to mitigate water shortages and rich well-being in area coastal regions, and can improve freshwater both in quality and quantity. But it still faces potential challenge related with the associated with the high energy consumption, particularly of the seawater reverse osmosis systems that consume between 2.5 to 4 kilowatt hour per cubic meter, and its associated greenhouse gas emissions and the environmental impact that produce the wastewater discards. So the goal of this study is to evaluate the techno-economic feasibility of marine eco-parks as maritime cluster coupled with wide energy converters, seawater desalination, and marine aquaculture industries to energize the blue economy in the area coastal communities of Baja California, Mexico. So to this end, we propose a marine eco-parks unit coupled with 3 models, wide energy converters, desalinated water production, and seaweed aquaculture to produce and sell electricity, carbon saving, clean energy certificates, desalinated water, fruit for human consumption. For this is a dry seaweed ulva, and carbon credits. The field site is located in the arid coastal region of Baja California in the northwestern of Mexico. And this area has the highest white power availability, and specifically in the figure on the left, we can see the results of the Iowaga wave handcast based on WaveWatch 3 with a regional resolution on 17 kilometers. In the other side, on the right side, we have we foresee with WaveWatch 3 in our local area with a resolution of 218 meters. So we passed 2 kilometers to meters, and we found particularly some different wave processes that amplify the wave power by wave energy focusing produced in the north side by the offshore reef, San Miguel offshore reef, and in the south region by the shallowing effect that produced the shallowing offshore ridge and headland. So we're gonna concentrate in both two sites, chosen sites. So the methodological, we apply a financial model based on technical and economical data, based on available literature. We calculate the cost and contribution of each different models to the marine eco-park profitability, and compare with the current with the future projected to the future 2030 year. Particularly, we evaluate the wave power availability based on a SWOT model results directly from simulated directly from yes, we calculate evaluate the wave power availability, and mixing calculate the extracted wave power from a joint distribution combined with the wave power based on two devices that previously in previous work we found that produce the best performance in the study area, particularly with Pelamish device is a attenuator device and overtopping wave dragon device. With this, we calculate the annual energy production, and we mix with economics data and calculate the CAPEX, the capital cost, and operation cost of the wave energy converters, desalinated water production, and seaweed aquaculture, and put this all in the model to calculate different financial parameters like the levelized cost of energy, net present value, return of investment, and payback period, and like shown in these equations. Okay, results. In the scenario number 1, we compare the single wave energy converters performance with techno-economic performance compared with the groups or arrays of WEX. As can be seen in the left side, we got it the levelized cost of energy and the net present value, and we found in this region that have in this chosen site have the less levelized cost of energy, but we got it. It's difficult to see, but negative net present values. So the investment produce losses and don't be accepted. But however, when we pass of one device by economy of scale by groups or 2, 4, and 2 respect the centralized energy scheme, we got it a positive net present values, and return of investment and period less than 20 years. So when we improve and mixing with seaweed aquaculture, we see that in all the case, when produce more than we produce seaweed, 25% of energy to produce seaweed to 100%, we see that improve all these different net present values, particularly Pelamis device produced in Punta Santo Tomás, all different positive values, with a return of investment and payback period 5 to 18 years, less than 20 years. That is less. But when we mixing with the desalination water, we can see that in all cases, don't produce net present value positive. So the project is expected to produce losses and must to be rejected. This is due the capital cost of high price of the high cost of the capital cost of desalination. And when we compare in the scenario number 4 with the roadmap 2021-2030, we can see that when we pass for the present 2021 to the future 2030, we see the improvement of the difference of the levelized cost of energy. This is produced because the installed capacity, learning rate of these devices, and of course the different devices adapted to the moderate, like Paco said, moderate wave power conditions. But you can see that in the 2030, don't entry to the fossil fuel range. So we need to begin for the future years improve these technologies. So conclusion, the contribution per couple unit to the marine eco parks was evaluated. In all cases, Pelamis device generate better performance than White Dragon. The financial evaluation showed that marine eco park economically viable is based on economy scale of many devices per plant. In no case, seaweed desalination be profitable. Seaweed aquaculture was the most profitable product, followed by electricity. And the comparison again, other power generation technologies shows that the wave farms developed the highest reduction in the levelized cost of energy projected to 2030. But of course, we need to continue. I invite you to begin to innovate and develop new generations and adapt these technologies to our conditions, our seas conditions, to be more competitive and entry in the electricity pool. So I invite you to see this work and many of other works, related works in the Mexican Center for Ocean Energy Innovation, Remar Group, and the Pan-American Ocean Energy Student Network, that you had at this website, or you can write me an personal email. Thank you very much.
Any question? Here.
Very nice talk. Really nice. I'm interested in this stuff. You mentioned that your power generation was from something called the Pelamis system.
Yes.
And you compare that with Wave Dragon?
Yes, compare. Yeah.
Can you describe anything about how they do their energy extraction? I'm curious about what these machines are.
Okay. Well, in the case of Pelamis, when we think in arrays to respect the decentralized energy scheme, why decentralized energy scheme in Mexico? Because the production energy you can see here is less than the competitive market, like traditional centralized scheme. So we need to get new opportunities based on decentralized, and in the case of Baja California, it's like an island. It's not connected to the national grid of energy, so we buy energy from United States. So we put arrays to produce mean wave power than as 0.5, that is the normal of Mexico to decentralized energy scheme. So you can see there how Pelamis device produce in this case two devices produce less in Punta Santo Tomás produce less than Wave Dragon, but when we compare the annual energy production, integrate this and mixing with the capital cost and operation, produce best reduce the levelized cost of energy, so be more competitive. Yeah. So and the annual energy production improve and condition the levelized cost of energy more than the cost and operation, the capital cost and operation cost. Yeah. Yes. We select like hotspot sites of maximum mean wave power. The impact? Wrong? Like currents or?
I'm thinking more in terms of engineering maintenance costs of a machine in a very hard environment. These two devices, we haven't seen any pictures of Pelamis versus Wave Dragon. I'm curious.
Yes.
Because we've seen dippers, we've seen flappers, we've seen a bunch of different machines.
Okay. The Pelamis device is a floating device. It's a worm. It's like a worm on four different segments.
Right.
You know, in Asadora in Portugal, they put two devices like web farms in arrays. And Wave Dragon is a overtopping. It's a, when focusing the convergence of the wave in one point.
Okay.
Pass with the chamber and produce energy. Yeah.
Okay. Thank you very much. That was what I was curious about.
I published in one journal this. We evaluate 8 different wave energy converters, and Pelamis and Wave Dragon produce the best performance. But of course, we need to begin with this concept to the future and improve to me more efficiency, getting more capacity factor. Of course, like say Paco, we need to develop small ones devices to be more competitive and less capital cost of investment, for sure.
Are they expensive? I mean, how expensive are they, the devices?
Well, in the case of Pelamis, is cheaper than Wave Dragon, and it's like one device is like 3.5 million, more expensive than the Alejandro device. But to me, it's not a problem. It's a problem for sure, the cost, but it's more determining the capacity factor for, of course. We got it in this condition. This device improved in the high latitude, like Scotia, with strong wave power.
Yeah.
But when we move and improve in this seas with a middle resource, it's not work too good or less. It's like if you have there like the 20% of the year work with a high capacity, in this is work like 20 with a less of efficiency. Yes, but this is a good comparison, because with this comparison we can improve new generation. For course, we need compare. Okay.
Thank you very much.
You're welcome.
Thank you very much. See you in the afternoon, 2 p.m. Thank you very much again.
It is lunchtime. The invitation is for the same restaurant as yesterday.
Hola Miguel, ¿me ves? Ah, pará, soy yo el problema, que no te estoy escuchando. A ver, háblame ahora. Ay, justo ahí viene el que sabe. No estoy pudiendo escucharlo a él. ¿Está ahí, lo ves? A ver ahora.
Ahora sí, yo te hablo.
Sí, ahora sí.
Sí. Ahora, bueno, hola.
Buenas, ¿cómo estás?
¿Todo bien? ¿Y ustedes cómo están?
Bien.
Ahí, bien, ¿todo bien? ¿Está yendo la conferencia?
La verdad, por ahora todo.
Okay, sorry for the hurry. I hope you enjoy the lunch. So it's time to continue with the next session. The keynote speaker is going to be Miguel Honorato. The session topic is nonlinear wave dynamics. So Miguel is going to give his talk remotely. Hi, Miguel.
Hello to everyone. Can you hear me well? Can you hear me? Can you see my screen? Hello? Can you see my screen? Can you hear
we
me?
listen to you okay.
Okay, so just tell me when I can start. Just tell me.
You can start.
Okay, you didn't mention. So I have half an hour? Is this the time?
Is it okay?
Yeah,
it is okay.
Okay. Just let me know. I mean, I can
half an hour for the presentation and also for some question and discussion.
So the whole is half an hour. Okay, let me start. Okay, go. Okay, so good afternoon to everyone. So welcome back from lunch for you. So I will talk about rock waves. Can you see also my mouse moving? Yes? Yeah? Okay. Maybe yes.
Yes.
So I will talk about rock waves, and this is the topic which I've been working a lot in the past, a little bit less recently, but let's say in the last 20 years I've been really work a lot on that. And so I will give a sort of review of what I believe are the relevant results in the field, especially, I mean, from a more general point of view. So, and I will discuss rock waves in deep water. I will not consider currents or any bathymetry, so it's really the simplest case that you can think of. Okay, so let me start with this. Okay, first of all, I can show you a picture. This picture was taken by Alessandro Toffoli while we were going from Cape Town to Antarctica on this Agulhas 2 icebreaker. And well, this is I'm not sure if this is really a rock wave, but in any case, it's for the picture. It's not very exciting, but I can tell you that if you are in the ship and things like that happen, you feel it a lot. Okay, because actually you see the ocean is not really you don't see big waves around, but then you get a couple of waves which are much larger than the other, and you make big splash. The impact is strong, and so this is basically what happened. So note that this picture was taken from 30 feet to 35 meters height. So it's quite a big wave that we encounter. Okay, so just the outline of my presentation. So I will give you an introduction to the problem of rock waves. And then a little bit of history, but it's going to be recent history in the sense that, as I mentioned, it's going to be history of about 25 years history, maybe 30 years history, no more than that. Well, before that is prehistory. And depending on how much time, how I'm going, I will just present some new measurements of the large wave packets. New is maybe it's not the correct word because the measurement has been done in 2014, but we just published a paper recently. So I will, if I have time, I will show you some results on that. And then we can have a short discussion with some conclusions and so on. Okay. This is an important slide, I think. It's this paper by Sergei Yanenkov and Viktor Shrida. I think is a little bit overlooked because it's about predictability of surface gravity waves. So when you want to talk about rock waves, the first thing that you want to ask is, can we predict rock waves? So that's the first thing that we should know. And this paper actually does not really is not really related to rock waves. It's just in general. So it's on surface gravity waves and gravity capillary waves. So they consider just dynamical equations, a Hartree equation. It's an Hamiltonian system, and they compute Lyapunov exponents. And what they find is that the system is chaotic. So this is something interesting that people tend to forget. And so you have, just like for the weather, you have a window in which you can do prediction. But after that, I mean, the system is chaotic, so you cannot make any prediction anymore. So basically, what they found is that the time of prediction is of the order 1/epsilon square, where epsilon is the steepness of the wave. So you can make prediction for maybe, let's say, 100, 500 periods and so on. But when you go to the 1,000 periods, then the system is definitely chaotic, and you lose information of your initial condition, right? So this has very important implications in the sense that you can make prediction on rock wave only on a statistical basis. Right, so you can do deterministic approach in the sense that I've been also working on that. The idea is you can place, for example, a radar on the bow of a ship, and then you look 2 kilometers outside. far away, and then you try to integrate some dynamical equation. I mean, you measure something, and then you want to integrate in space and time your evolution equation up to your target, your position. And if you can do it faster than the waves too, then you have done a deterministic forecasting, okay? With all the difficulties that you get in that. Of course, this can happen if you are away like a few hundred periods, but then for larger time, then this approach won't work. And then, of course, the question becomes, what is the probability of finding a wave that is larger than, for example, 2 times significant wave height? So this is what people have worked for the past not only 25 years, but since the work of Longet-Higgins in the 50s. Okay, so when you want to talk about, you want to do a review on something, you just go to Google Scholar and you click and you write rogue waves, and then you get 66,000 results. Okay, so it's the literature on rogue waves is really huge. And it's not, as I will just mention, it's not just only on water waves. I mean, in the beginning, the problem was only related to ocean waves, but as I will show you, many other fields, and this has been a very interesting part of our work, to talk with people coming from different communities working in different subjects like nonlinear optics or plasma physics or Bose-Einstein condensate, with whom we could exchange ideas, and also they could take our ideas and think about rogue waves in other environments. For what concern water waves, there are probably more than that, but I have seen 5 relevant reviews. Okay, starting from the one by Muller, Gavet, and Osborne in 2005. And then the last one is this 2019 is a modern view. It's John Dudley, Kenty, Musso, Shabshub, and Diaz. I think Frederick is there. And you see just the last one is rogue waves and analogies in optics and oceanography, which means that, I mean, you see the 3 first author of this review actually come from the optical community, and Shabshub and Diaz are from water waves. Okay. So this gave us really, for some of us, like Frederick or Amin, the opportunity really to exchange ideas with other people, and I think that made very rich our topic. Okay, so if you want to make a review on rogue waves, you cannot avoid to put this picture, because I think this should correspond to year 0. So 1994 corresponds to year 0. Because all started with this measurement of the Dropner wave in the North Sea. This was done by Sede from the Statoil company. So using laser, looking down laser, they measure the surface elevation, and they measure this huge waves, 25, the wave height is 25, 26 meters, significant wave height of this is just wrong. Significant wave height is about 12 meters, so it's sigma is the standard deviation is 4 meters, and so on. So you have the length using dispersion relation is 320 meters. So it's a huge wave that is traveling at 80 kilometers per hour. And if you look at its age with respect to HS, is 2.1. So this is classified as a rogue wave. Okay, so everything started here in 1994, and this was for some year actually these people were not aware of this measurement, but then in Norway people start looking at it, and indeed I think that there has been a number of pioneering papers and work on the subject. Indeed, in 1997, and this was I give the credit to Trulsen and Diste, who started looking at this wave, using nonlinear Schrödinger equation, which is a modulation equation that describes waves in a narrow band approximation. It can be one-dimensional or two-dimensional. And so, indeed, they have a paper, and actually it's a proceeding in which, in 1997, in which they write explicitly, and I like to read this for you. We seek to understand the occurrence of Frick waves by nonlinear self-modulation or of a slowly modulated weakly nonlinear wave train, which basically means nonlinear Schrödinger equation, for which ocean recurrence or non-uniform bottom topography can be neglected. I mean, this means that they are not looking at other effects like interaction with currents or bottom topography, and they present field observation, which is actually this Dropner wave, and suggesting that the wave condition leading to freak wave can be described as a narrow banded weakly nonlinear wave train. So I think this started, I mean, everything started from here in the sense that they were the first, and this follow, a lot of people follow this idea of looking at modulation theory, trying to understand nonlinear Schrödinger equation. Indeed, a few years later, I mentioned 4 papers here, maybe there are some other that I'm forgetting, but 4 papers in which they actually discuss exact solutions of the nonlinear Schrödinger equation that resemble rogue waves. And then in the past, before, I mean, the nonlinear Schrödinger equation was an equation known from the 60s, so it's not new in the community of nonlinear waves or in the physics community. And also, analytical solutions, since in 1D this is an integrable system, can be found. Then what was, I mean, discussed in these papers, these 4 papers that I mentioned, the fact that some analytical solutions, which I plot here, resemble rogue waves. Indeed, those waves correspond basically to modulation, to modulation and stability. Okay, so I mean, there is a connection between this analytical solution that you see on the right-hand side to the modulation and stability theory, which is a modulation of a plane wave solution in deep water. And there are different kinds, you can be periodic in space. I mean, it has a really a zoology of solution, the MLS equation, very interesting. Actually, is a field in itself. I mean, it has become, after this work in our field, it has become among mathematicians really something that, looking for solution, analytical solution of NLS that have amplification factor of 3, 6, 9, and whatever has been becoming a sport. I mean, literature is full of those kind of solutions. Probably the most interesting, or one of the most interesting, is the Peregrine solution, which is this one that just appears 1 and then disappears, just has amplification factor of 3. But in any case, those are all deterministic solutions. So people have started working on the field, okay, and after that, and the interesting thing is it was a huge boost from the optical community. This paper came a few years later, 2007. It's a Nature paper, so it has a big impact on the literature. And interestingly, I mean, this paper is called Optical Rogue Waves. Actually, what they did, they use a laser, they use an optical guide, wave guide, and they make measurement, and they were able to observe some extreme large intensities, and so they used the word rogue waves, and this started the connection between oceanographers or people working on linear physics and people in optical and nonlinear optics and so on. So you see that the number of citations from Google Scholar of this paper is 2,431. So it's a really huge number of people are working in optical rogue waves, more probably than in waterways at the moment. Okay, so this was basically the idea, but now we can also go back to the statistics. As I mentioned, water waves, I mean, if you want to understand the wave, the rock wave formation, if you want to understand, I mean, do some forecasting, the possibility that you have is just to know the probability density function rather than look at the deterministic evolution of the waves, right? So if you want to make something that is prehistory, you have to go to the paper of Longet-Higgins, 1957. And the idea is very simple. I mean, whenever you measure a time series in the ocean and you look at the phases, you can see that the phases are uniformly distributed. I mean, it's hard to find any correlation among the Fourier phases, right? And then if the phases are random, then because of the central limit theorem, then the distribution, the surface elevation can be distributed according to Gaussian distribution, which is here, P of theta, this is Gaussian distribution. And you can show that in a narrow band approximation, so narrow band approximation, the Rayleigh distribution holds, okay? So this is something that people know known since the 50s, okay? Or you can also compute the survival, the probability of accidents, so which is an integration of this from 0 to HC, okay? And so this is the probability of exceedance. And if you define a rock wave here at 2 times significant wave height, then the probability that does occur is 1 over 2,980 waves. So basically, this is all linear. Linear waves explain perfectly rock waves. Okay, so there is nothing wrong with this, because you just have to wait long enough. If you're sitting on a boat, if you're sitting on a buoy, you just wait 3,000 waves, and you will encounter a wave that is larger than 2 times significant wave height. Nothing wrong about that. That's as I would show, is the most common thing that happens. However, I mean, things can be different. Okay, so I remember when in 2001 we started doing some numerical computation of the NLS equation. Now it's called TNLS, time-like nonlinear Schrödinger equation, or Dijkstra-Lomé equation. And what actually we observe is that if we include nonlinearity in one dimension for waves propagating in one direction, actually, if your spectrum is sufficiently narrow, so those are runs that are made using Jean-Swan spectrum as initial condition, and if your spectrum is narrow enough, then what you observe in the statistics is that the continuous line is the Rayleigh distribution, and the dots are just come from numerical computation. You see that there is big deviation from the Rayleigh distribution. So this implies that actually one-dimensional model like nonlinear Schrödinger equation, that would be the same if you do Euler equation. Of course, not exactly the same, maybe a little bit more or depending. But in one dimension, you get these extra tails in the probability density function, especially if your spectrum is narrow and your steepness is large enough. Okay, and this after that we did also experiments, not only numerical computation. These are experiments that were done also in collaboration with Gigi Cavalieri, Stansberg, and Brandini, Osborne, a number of people. And then Peter Janssen came in 2003 with a nice theory. So those are our experimental data, and this is the theory developed by Peter. That's also, again, it was very interesting to follow his theory, because this gave also a lot of insight, not only on the freak wave problem, but also on the kinetic equation, on the role of quasi-resonances, and so on. So this was also a very important paper in the community, maybe not only for oceanographers. Okay, but what happened then? Well, I'm going here is more or less I'm going with years. So now this is now 2009. Okay, I can 2009. We went to a large basin with now its basin is not anymore a wave tank. So we had a basin and with a directional wave maker, and we started doing experiment with the directional waves. Okay, this is again in collaboration with Gigi and other co-authors. And well, of course, in the case, these are just different distances. So you start with random phases, some Johnson spectrum with some gamma. You let the system evolve along the tank. These are just different probability and survival functions, probability of exceedance along the tank. Again, this is for the one directional case, and you see deviation from Gaussian statistics. However, interestingly, well, not interestingly, but okay. First of all, I forgot to mention something, that this tail that we observe here, okay, is something that I forgot to mention to make connection, is this tail is related to the, can be related to this kind of analytical solution of NLS equations, which are called breeders. So the breeders populate the tail of the probability density function. I mean, I could be more precise in this statement, but this is more or less what happened. So what we thought is that this tail was the result of some sort of modulation and stability analysis. But if you increase directionality, so we did experiments again in this large wave tank, but this time what we did was that we used a Johnson spectrum, but with a cosine to some power n, in order to put some directional spreading in our data. And what happened is actually modulation and stability is completely killed if you have, we put NA equal to 24, for example, and we get, something that the Rayleigh distribution does a very good job on our data. Okay, so this was already 2009, and before that, 2004, I had a numerical paper on the subject with also contribution from Dijkstra and Trulsen and so on. So that was I mean, this is well understood already in 2009. But what about crest distribution? So I think this is also an important thing to discuss, because there are many people who are working on crest, and this is not the point where I mean, if I start mentioning somebody, I should mention all of them. But I just want to mention the typhoon distribution, which was made around in the 80s. So the typhoon distribution is a distribution for the crests. But what many people do not know about this distribution is that it's an upper bound distribution. So it's an upper bound. So it means that the tails, it's a maximum that you get at the tails for actually second order Stokes-like wave solution, okay? Because with the slowly varying. So the idea is the following. I mean, you have of typhoon, you have a narrow band approximation. So you have a wave packets basically. And in this case, so the amplitude is a function of x and t, and this is just the Stokes expansion in the case of slowly varying amplitude. So this is the second order correction. Well, what Typhoon did simply is just, okay, let's put cosine equal to 1. What is the maximum that this function can be? Cosine equal to 1, cosine to 2, theta equal to 1. And then you have the distribution for the amplitude, which is Rayleigh distributed, and then you compute the distribution for eta. Okay? So this is just the thing that has been, I think it's a brilliant idea that he did, but don't forget that this is an upper bound distribution. And again, I mean, if we go in the narrow band case, again, modulation and stability, and you see a lot. So the dashed line is just the Rayleigh distribution for the crest. The continuous line is the Typhoon distribution. And those are different plots which are made at different distances from the waymaker. And you see clearly that as you move along, from the waymaker, you get deviation from Typhoon distribution. This is a case of gamma equal to 6. The plots in second row are gamma equal to 6. You see these big tails are forming here. Okay, but this is for long crested waves. But as soon as you go to short crested waves, again, the Typhoon distribution does quite a good job once you increase the distribution, the directional spreading of the data. Okay, so this is what was done in wave tanks. These are all experiments that were done. Published in 2009, and then it's worth to mention this work that has been done by Fedele, Brennan, Sonia Ponce de Leon, and Jean Dudley and Frederic. Yes, and in which they measure. Well, not they measure. They consider. Well, the title is a little bit a real world ocean rock waves explained without modulation and stability. Yes, of course, we can explain rock waves without modulation and stability. Indeed, what they did, they took the three rock wave measure in the ocean, which is Andrea wave, which is also in the North Sea, Dropner wave, and the Keynote wave. And what they did hindcast of the storms in which this wave had appeared. And then in this way, they were able to get the spectrum at the time of the measurement, the directional spectrum, and they used that to feed what is called a higher order spectral method. So using random phases, they used that spectrum to evolve now in a deterministic fashion the evolution equation for water waves, basically the Euler equation. So this is what they did. And then they compute using ensemble averaging. They compute the probability density function. And what is clear from here, I mean, here they have a T, R is Rayleigh, T is Typhoon, and this is TF, I think is third order Typhoon. Okay, this is just the inverse of the exceedance probability. And so it's return period. It's very similar plot as the one that I show. What you see here, this is the dashed line Rayleigh, and here you see the data that are well captured, except for some points up here. For example, some points are up here, which are not completely captured, but it's not clear if this is just outside the, I mean, without an error bar, it's hard to say if this is fits or not. I mean, and here, so the idea here is that, as just in the tank experiments, ocean waves have directional spreading, and this is natural. So for most of the time, I mean, this is the second order distribution fits quite well. Just remembering that that is an upper bound distribution. It's not just a regular second order distribution, but it's an upper bound distribution. Okay, so it's on top of all the other distribution for second order. Okay, so this was more or less my, my idea on rock waves today, after many years of discussion. Of course, this is only related to deep water. Just now briefly, I will be very, very brief on this because it's already, I think I have 5 minutes more. I would like to present you these results that we published recently in a paper with, also with Gigi and other collaborators, with Alvise and then a group of Spanish people. And the idea is that, I mean, they got this measurement from a buoy, which is this huge wave here. This is a huge wave packet that has been measured. And if I zoom it, I mean, the HS was 11 meters and peak period of 18 seconds. So very, very, very long waves. Indeed, what the exercise we did here is to plot in the same plot the Dropner wave, which is the red one, and this huge wave packet that was measured by the buoy. So you see how big is, I mean, probably not the height. I mean, this is the crest, not the crest. The height, yes, but not the crest. Because the crest, we have to think also that this measurement was done using some buoys and not laser like in the Dropner wave. And those waves are really, they have a wavelength of 540 meters. I mean, it's huge wavelengths. And not just a single wave satisfied the rock wave criterion, but I think just 2 or 3 of them. So the whole packet is it's much, much bigger than the rest of the packet. It's a huge amount. It's a volume water. It's tons and tons of water traveling at the speed of 100, I mean, phase velocity, 110 kilometers per hour. That, of course, breaking of this on some structure would be a very devastating effect. What I show here is just the movement of the buoy. So it's some sort of Lagrangian motion. The black line corresponds to the time in which a huge wave was measured. And as you can see, it's on a line. So this basically means that the wave was almost unidirectional. I mean, waves were not coming, this crest that you see were not coming from different directions. The conditions were basically a swell. You had a long swell and then some wind sea, probably is clear here. This is a directional spectrum, was computed by Alvise, Benetazzo, in which you see here this is the swell peak, huge peak, and then you have here another peak, a small peak, and this which is related to the wind sea, generating wind sea. And those are the meteorological conditions, but I don't, maybe Gigi Cavalieri will, if he wants, you can ask him where exactly, but you see a big storm forming here and going down towards the Peninsula Iberica. And here is the place where it has been measured. This is the place of the board. So, okay, now what we did with that, I'm just jumping, just to finish this. Okay, so what we did is that we assume that this wave packet is just described by the nonlinear Schrödinger equation. I mean, of course, this is a big assumption. Okay, it's a big assumption. Because the nonlinear Schrödinger equation is integrable, then there is a whole theory developed, which is the inverse scattering theory. I don't want to go into the details, but the idea is that you can associate an eigenvalue problem to the nonlinear Schrödinger equation. Okay, so this is the eigenvalue problem. Psi1, Psi2 are the eigenfunction, lambda are the eigenvalues, and A0 is the time series, that it's the envelope of the time series, okay? And then what happens is these lambdas, if you, according to the theory of NLS, do not evolve in time because they are constant on motion, and you can compute those lambdas, and this is actually what we have done. So we have window, our time series here, and if we compute this is the nonlinear spectrum. So this is a nonlinear spectrum. If you have dots in this imaginary part of lambda, it means that you have soliton-like components, those nonlinear components. So we did this exercise in a window here containing the huge wave packet, and we get some nonlinear content. So this gives us the idea that actually the wave was really nonlinear. And then we just to check that everything was okay, we also did it on different windows, and then you see nothing, so no unstable, no soliton-like structures. Okay, so that was more or less the conclusion. Of course, the assumption is big, but we all know that, I mean, those kind of waves cannot, if they are one-dimensional, they cannot survive forever. So actually, we're trying to estimate that using tools from NLS in 2D, and we expected that this packet, I mean, this is very, I mean, it's not rigorous, of course. It's just an estimation. Could have a lifetime of order of 20 minutes and so on. Okay, so basically, I'm done. I'm done. This is my last slide. So, I mean, I gave a discussion of rock waves, but I have not discussed many things in half an hour. It's impossible. With current interaction, there's going to be a talk, I think, after. I didn't discuss any probability distribution based on fitting parameters. People like to, put a Weibull or a Forrestal distribution, try to fit parameters. Cross-NC states are also important. Huge problem related to mathematical aspects, solution of PDEs, damping, forcing, all that is something that maybe we don't know enough. Finite water depth, no bathymetry. I mean, I just really consider the simplest conditions. Although I gave contribution also, I published some papers also on other of these topics. Just the last, these are just collaborators. I'm sure I missed somebody. I'm not. I collaborated with. I had really. On rock waves, I really had the opportunity to work with a lot of people, and that made really good time for me to learn a lot from other people from, as I mentioned, nonlinear optics, like Wavenitz, or mathematicians like Lombardo, De Gasperis, and so Akhmediev. So it has been really 20, 25 years of really good time doing research. Okay, that's the end. Thank you. Sorry for being late.
Thanks, Miguel. Questions?
I hope you didn't have a siesta for my talk, right?
Ciao, Miguel. Gigi.
Gigi. Hi, Gigi. How are you doing?
Sorry not to see you here, of course, but you are a busy man. We know that.
I just teach. I just have to teach.
Okay. The beautiful landscape of what we know about the deep water, no current, these sort of things. And do you think that you are one of the best who's work on the subject? Thank you for mentioning all these people and myself. But how far further can we go with the theory, for instance? Do we ever, because in my personal experience at sea, I've seen 2 freak waves, and they seem really out of the blue. Actually, one, neither of this, one was studied with Al, of course, the original one with the big swell. The other one is something that we saw on the tower that we don't even, something like a 5-6 meter crest out of 2 meter significant wave height. We have optical evidence by the video camera. Do you think we are at the frontier now of what can be done, or there is some further physical aspect to be found into the sea? Without mentioning all the special cases that you mentioned, or the shallow water currents, these sort of things. That's my question.
Yeah. Okay. So, so there has been really done a lot of work, theoretical work and numerical work. So numerical work, I didn't mention. Many people did really Euler equation simulated with a high accuracy, Navier-Stokes equation. So there has been really huge amount of work on the subject. What I believe is really missing is our knowledge, or maybe my knowledge. I mean, maybe you have done. I haven't followed the literature, but on directional properties of the spectrum. What I mean is that what is really important to, I mean, the linear theory is fine, and it works perfectly in most of the cases, right? And this is what we know. However, for example, I mean, we recorded some data with Toffoli in Alberello during the cruise using this system of Alvise with two cameras. And we recorded really tails in the probability density function, which are far away from Gaussian, far away from Rayleigh distribution. So there are situations in the ocean in which things are not Gaussian, are not linear. So there are situations, maybe less. I mean, rock waves can be, come from both of this physical, either interference, linear superposition, or nonlinear one. But what we're missing in order to understand the difference in between the two cases is a directional spectrum. I don't know how far now we can measure in transverse direction. What I'm saying is that we don't have enough measurement, I think, in transverse direction. We don't have, let's say, the spectrum computed on a 2 kilometers by 2 kilometers region. And I would love to see that, because that would give us really an idea of what is the spectrum transversally. And as you have seen, this is very important for rock waves. I mean, to distinguish which is the mechanism for generating rock waves. Sorry, I mean, I could talk more, but I probably should stop here. Yeah. Did I answer, by the way? You're still there?
Wait a second.
Hello?
No, in fact, there was also something else I was going to ask Miguel. And for instance, I remember when it was Trulsen and the other Norwegian people, when there was the Draupner wave, they showed how they could evolve the time series, of course, up to set one. And the question is that if we had, say, a few kilometers of 5 minutes of wave before the freak wave appear, would we be able to see it or to guess that a freak wave was coming? Which is a time scale, as a space scale, we could work it out.
Yeah, I mentioned, I mean, according to if we have one-dimensional measurement, there's nothing you can do. I mean, one-dimensional measurement, it's nothing. You should have a measure on a surface. So I think that's the most relevant thing if you want to make some forecasting. But I mean, we believe to the paper by Schrieder and Annenkov, then we can make deterministic forecasting for 100 periods. So maybe 100 period before you could see it, and if you know the speed of the wave, you can know how many meters or kilometers has propagated that. So, but then those things, yes. You can forecast it before, but then of course the focusing can be in a very short time. I mean, focusing can happen in time of scale of maybe depending on the size of the wave, but in a very short time. You see, when we're doing experiments now in the wave tank, maybe everything was happening in 10 meters. I mean, we had a 100-meter wave tank and everything was happening in 10 meters. So that's a focusing process. But if you want to forecast, you could. The wave packet, you could measure it also maybe a couple of kilometers before.
Hello, Miguel. Nice to see you.
Yes, who's speaking?
This is Paco.
Paco.
Miguel, thanks.
Hola, Paco.
Thanks for your presentation. Really nice, interesting topic always. Yeah. My question is regarding this kind of basic theory, and can we get in any way a rock waves numerically from the very fine directional spectrum, making
yes.
the inverse Fourier transform? Is it possible to get one, or what do we need to include? I know that talking about the directional spectrum is simply thinking that the monochromatic waves are superimposed one above each other, right? But then
yeah, of course. I mean, it's possible, of course. I mean, to answer your question, it is possible to do numerically. I mean, if you have a directional spectrum, to have a rock wave. That's very. I mean, as we mentioned, I mean, we're talking in a statistical context, right? So rock waves appear also in linear dynamics. So even if you take a linear dynamics of the surface elevation with some directional spreading, you will get a rock wave. You have just to wait 3,000 periods, okay, and you will get a wave that is 2 times significant wave height. So there is no. The problem is that if you want to have something that has a probability, larger probability, then you have to include nonlinearity. That's and you can do it. I mean, you could have modulation instability, but the question is how narrow must be your spectrum in direction in order to have modulation instability possible in the system. And I think this is what we're missing.
Right. Thank you.
Thank you, Pablo.
Alex.
Miguel, thank you for the talk. That was a very nice overview. But you see where this a audience getting, right? The question of Paco is about the spectral environment, right? And of course, directional thing is directional spectrum is part of that. But even directional spectrum, it's not the same as a quasi-monochromatic wave trains, unstable to something, right? And you actually started this topic. I'm talking about your paper of 2001, right, where you introduced the instability of the spectral environment, right? And now you didn't even mention that, right? So, Miguel, you changed your views, or what's the situation here with rock waves in the full spectrum environment?
No, actually, what we did in 2001 is still valid. I mean, those numerical computations are made in about 2001. It's not on the paper, but this numerical computation in which you see the instability of the Jones-Watt spectrum is still there. But and you see this big tail that is forming out of you have a Jones-Watt spectrum with some gamma and some steepness, and you form this tails. Okay, that's perfectly fine. But this is a one-directional thing, right? If you start putting to also directional spreading, so you multiply your Jones-Watt spectrum by a cosine and theta, and then you do the simulations, and then this tail, if your directional spreading is large enough, it will reduce to the Rayleigh distribution. This is what it happens. So whatever I have said is true for one-dimensional propagation. But the question is that we don't know, especially at the peak of the spectrum, how narrow is our ocean wave spectrum. Okay, we don't. I mean, this is my feeling, is that we don't know. Our accuracy is very. I mean, it's very poor when we start talking about the distribution around the peak. The tail of the spectrum transversal is fine, but around the peak, and that makes really the difference between something that can be unstable to modulation instability or not. Okay, so yes, I still believe what we have done is correct in the sense that it has been verified by many other people in wave tank and numerical computation. So I still believe in what I have done.
Hello, Miguel. I'm Leandro Fernandez. Remember me from Cayuleven?
Yes.
Yes. Well, remember we work with time fund distribution and some comparisons. My question is, if you know or you have been working lately in a new distribution in order to capture the higher order of nonlinearity more than second theory. Second order, sorry.
Okay, so yeah, yes, okay. So typhoon distribution is a second order theory, but it can be also a third order theory, but it's all based on Stokes expansion. So it's bound modes. So typhoon just works for Stokes like waves, right? Modulation and stability. Well, there are other distributions, but I am not really fond of working with distributions in which you have to fit. You have fitting parameters, right? The people work a lot with waveful distribution or horizontal distribution, but I mean, either there is a physical insight in there, but just having an equation and two parameters and you want to fit them, I try not to do it. I mean, I know that it's important, it's relevant in the engineering for designing structures. So I'm not saying that it's not a good job, but what I'm saying is that I prefer not to do that. Peter has work on in deep water has work, and actually this is his nonlinear theory that is based on the calculation of kurtosis that works well for also in these strongly nonlinear cases. In the weakly nonlinear cases or in the linear case, it's just reduced to the standard typhoon, or because it's the linear case, you know, the kurtosis is equal to 3 or equal to 0, depending on how you define it, and then you get the standard linear distributions. So, yeah. So the answer is not. I haven't worked with other distributions.
Okay, thank you very much.
Okay. Thanks, Miguel, for your nice presentation.
Okay.
It is time to continue with the next speaker.
Okay, I wish a good conference now. Ciao to everybody.
The next speaker is Carl Burr from the Universidad Federal do ABC, Brazil.
Thank you very much for the introduction. I'm Carl Burr from the University Federal of ABC. I'm happy for
the microphone, please.
I'm happy with the opportunity to give a talk here. So I'm going to talk about weakly nonlinear fully dispersive water wave model. So I will give an introduction, then a concise literature review, talk about the conformal mapping approach that I'm going to use, show the governing equations in dimensionless form, and then the conformal mapping settings, and show the equations in the mapped domain. From that, I will obtain like a non-local formulation, and this will be useful to obtain like simplified wave models. Actually, I'm going to present 3 models, like a weakly nonlinear fully dispersive wave model that actually gives the name to the talk, then a weakly nonlinear and weakly dispersive wave model, and a linear wave model. Okay. So here's like the setting. Okay. X and Z are the horizontal and vertical coordinates. At of X and T is the free surface position. Minus h of X and T is the bottom position. Okay, the bottom here can vary with time. Lambda is the wave length scale. A is the wave surface displacement length scale. A tilde is the bottom vertical variation length scale. Capital lambda is the bottom horizontal variation length scale. L is the size of the variable part of the bottom. H0 is like the depth in the uniform part. So, like in the literature, like conformal mapping applied to this kind of problem, there's like basically 3 approaches. The first one is actually a double channel, like a strip is mapped in the domain bounded by the bottom and its image with respect to the undisturbed free surface. The second one's like I call like a I call like fluid domain. The strip is mapped on the fluid domain. It's actually for like nonlinear waves, like it's a time variable bottom, time variable conformal mapping. And the other one is like a composition mapping. The idea is actually to map a strip in the domain bounded by the bottom and its image with respect to the free surface, the separate free surface. And then another map that actually maps the region bounded by the free surface in this simplified domain into a strip. Okay, then here in this situation, like the bottom of the free surface is flat. The second mapping here is like time dependent, and the other one is only time dependent if the bottom varies with time. So what's the advantage of this conformal mapping? Simplifies the bottom boundary condition, simplifies the geometry, and this simplified geometry, like Laplace equation, has an analytical solution. So here I will present like a concise literature review of the application of conformal mapping to wave interaction with one-dimensional bathymetry. So the first application is like numerical simulation of fully nonlinear water waves. Basically, there are two approaches, like a single time-dependent mapping, like Viotti et al. 2014. But this one has an advantage because at each time step, for example, in this paper, it uses like a pseudo-spectral method. Each time step, it actually has to, the depth profile has to be updated since the mapping depends on the free surface displacement and the bottom. And this one here, like a composition of two mappings. The first map flattens the bottom and the second flattens the free surface. In this approach, it doesn't have the advantage of the first one. Okay. And actually, for like conformal mapping has been used also for like a study of linear wave localization, interacting with like in the localization phenomena in the linear water wave interaction with rough bottom bathymetry, like in 1995. For interaction of linear waves with periodic bottoms, then you can actually obtain like an exact solution for this problem using flow K theory. And then we have like better prediction for Bragg scattering and higher order Bragg scattering. And examples of this work like Howard and Yu and Howard 2010, 2012, Yu and Zeng 2012. And actually the earliest application of conformal mapping for this problem is like to obtain like simplified wave models, like shallow water and Boussinesque type models valid for like variable bathymetry. Example of this work like Hamilton 1977, Nakbin 2003, Munoz and Nakbin 2006, Focus on Nakbin 2012. Actually, this is interesting work because it uses conformal mapping to simplify the geometry, and then uses that integral relation that involves like the boundary values, and they actually they use this non-local. Then they obtain a non-local formulation, and use this non-local formulation for obtain like under the hypothesis of weakly nonlinear regime and weakly dispersive regime, like a simplified wave model. So here in this work, my work here can be seen as extension of Fox and Nakbin 2012 to time-dependent bathymetry, because they restricted themselves to only to time-independent. So here I include the case for time-dependent bathymetry. So we assume like an incompressible fluid rotational flow, then the velocity can be given by a potential function. So I have like alpha is my horizontal length scale, beta my vertical length scale, C0 is my velocity length scale, is the shallow water velocity, A and A tilde are the free surface displacement and bottom vertical length scales. So here's like my non-dimensional setting. Then I have like two non-dimensional parameters, epsilon and delta. Epsilon is the ratio between the free surface displacement scale and the length scale, and delta is the ratio between the vertical and horizontal length scale. So here's like my boundary value problem, Laplace equation, the dynamic free surface boundary condition, the kinematic free surface boundary condition, the bottom boundary condition, the kinematic bottom boundary condition, and assume that at infinity the fluid is at rest. Here's like the free surface curvature that actually shows up due to surface tension effects. Sigma bar is the free surface non-dimensional number. Well, non-dimensional number associated with the free surface. So from this point on, all the variables are dimensionless, and the bar will be omitted. So here's the mapping that I'm going to consider. Like I'm going to map a strip into the region bounded by the bottom of its image with respect to the undistributed free surface. So here's the physical free surface, and here is the mapped free surface, and the bottom is flat. So here's like the Cauchy-Riemann relations for this mapping. The free surface in the simplified domain is mapped in the physical free surface. The flat bottom is mapped in the variable bottom. Here's the Jacobian of the transformation with respect to the imaginary part of the mapping and its derivative, and here written in terms of the real part of the mapping. So in the strip domain, I have like Laplace equation, and then the dynamic boundary condition of the free surface assume this form here. And this is the kinematic boundary condition of the free surface, the kinematic boundary condition at the bottom, and the fluid that rests at infinity. And here's the free surface curvature. The terms in the equations with the red color, they show up because of the bottom can vary with time here. Okay. So now I'm going to obtain like a non-local formulation from the boundary value problem in the simplified domain, yes? So I define like a potential restricted to the free surface and the tangent velocity. And then I'm going to use the kinematic boundary condition for the free surface and the tangent velocity to express the vertical and horizontal fluid velocities in terms of the free surface displacement in the mapped domain, the simplified domain, and the free surface potential. Okay. And then I take the time derivative of the free surface potential, substitute this into the free surface, use the expressions for the vertical and horizontal velocity in terms of the free surface potential and the free surface displacement, obtain the first equation for my non-local formulation, the partial differential equation, in terms only of the free surface potential and free surface displacement. So I need a second equation. To get the second equation, I will consider like a function psi that satisfies Laplace equation and an integral relation, like and this integral, the domain of integration is actually the fluid domain here, bounded by the free surface and the flat bottom. Okay. And then apply divergence theorem, the normal vector to the bottom, normal vector to the free surface, and the boundary value problem, boundary values, and then I got like this integral relation here, involving the free surface potential, the function psi, the free surface displacement. And now I will specify the form of the function psi, like this one here, like with positive sign and negative sign. And then substitute this in this equation 24, obtain two equations, subtract them, and then I can reduce this, obtain this integral relation here, only in terms of the free surface potential and this free surface displacement. So this is the second equation for my non-local formulation. So here's like the non-local formulation. Well, this is actually hard to use for numerical simulation, but it's actually useful to obtain simplified wave models. So to be able to compare with the results from Focus and NACBIN 2012, I will make a change of the parameters. Like, actually, I will like define the vertical scale as the water depth in the uniform part of the bottom, alpha as the wavelength scale, and then I define new parameters, nu as the free surface displacement by the vertical scales, that's the depth in the uniform part. And then epsilon is written as like, oh, actually, my delta parameters, actually, I will label it as mu. And then epsilon is written as mu times nu. Okay, and then the non-local formulation in terms of new parameters, assume this form. So to obtain like my first simplified model, I will assume like weakly nonlinear regime, then mu is very small. So what I do, I'm going to actually, all the quantities evaluated at the free surface, I will expand in Taylor series to the order u squared. And since my mapping is like symmetric with respect to the undisturbed free surface, like zeta is equal to 0, all these derivatives of the mapping functions at the zeta equal to 0 at the undisturbed free surface, they are 0. So then the quantities of interest assume like are listed here in equation 28, like the expansion for them. And I have this hyperbolic sine and cosine terms in the non-local formulation. So under this hypothesis, I can expand them in this way. Okay. Then I substitute, well, and one more thing. Under this hypothesis, I have like a linear relation with the physical free surface displacement and the free surface displacement in the simplified domain. Okay. And then I use this fact, these expansions and this fact to rewrite my non-local formulation equations. So the first of the equations assume this form here, valid up to order nu squared. And the second one, this integral relation here. Okay. So actually, I will define another function psi, like it's time derivative of the free surface displacement. And then I have, so, and here, and then I will take so if I go back to the previous slide, this second equation, it's basically a Fourier transform, yes? So I will write this as a Fourier transform. Oops, okay. And then what happens? So it's differential equation, partial differential equation, okay? And here's like can be seen as like an algebraic equation in the wave number space. So then I have a system of partial differential algebraic equations, and this one has like index 1 with respect to time. What's interesting here is like it's written in terms of the free surface potential and the actual free surface displacement in the physical domain, eta. Okay. So now I can do one more hypothesis. Assume that the weakly dispersive regime, like mu is much less than 1, long waves. So I can actually use the results from equation 28, but then I can, like the hyperbolic sine and cosine, I can rewrite them, expand them in this form here. Okay. Substitute these results into my non-local formulation. Disregard terms of order mu fourth, mu squared times nu, and nu squared. And then the second equation can be integrated by part, and then it results like these two partial differential equations. This kind of, they are like Boussinesq type system of equations. And finally, I can actually linearize my weakly nonlinear wave model and obtain like a linear wave model. Okay, that has this form. So all the terms like in red in the equations are the contributions from the fact that the bottom varies with time. Thank you very much for your attention. And after that follows like the references that I used, that I cited before, above. Open to questions.
Questions?
Carl, it's Alex, I'm here. Congratulations, impressive mathematics, right? And what I'm also always thinking about mathematical theory, that mathematics, once it's proved, cannot be wrong, so it's always applicable, right? This model is having the time variable bottom, right?
Yes.
So I've been thinking, where can it be applied, right? So one thing which comes to mind is mud, right? If it's liquidized, the waves can be forced on the mud, right? And that's one environment. And in this case, waves propagate in mud, then your time variable bottom is actually periodic, which may be leading to some simplifications here.
Oh, okay.
But my question is, it's time variable, but can it be converted into space variable? Then it's any bottom, right?
It's time and space variable, yes.
Okay.
And the idea was to maybe like application like tsunami generations, maybe you can study that. And actually, if you want to study nonlinear waves with like a non-uniform bottom, then you can actually use the bottom to generate the waves to interact with the other parts of the bottom. So that's was one of the things that I was thinking about.
All right. Thank you.
Leandro?
Carl, tremendous work. I'd like to ask you, you presented these models and the nonlinear, weakly nonlinear and fully dispersive one. Could you comment on how could you get the actual solution since you have this bottom which is time dependent, and how can you concept this spectral method for the solution to get the actual solution to the model? Actually, I'm working on that. Actually, I was hoping to have some results to present here, but I don't have. The idea is to use a spectral method and to discretize in space, yes. So work in the wave number space. I'll come back and forth to the physical and wave number space, because I have like this convolution terms here, okay, in this equation. Yeah. And then actually to move in time, use a predictor to corrector method. So I can like differentiate this equation here and use like a bootstrap method to actually move in time to give a prediction, and then use like transform this in a iterative scheme to make like a corrector method. So that's the way I'm thinking to actually do a numerical integration in time for this system of equations, like for like variable bottom in time and space.
Okay, thanks, Carl. Nice presentation. It's time to moving on.
Okay.
With the next speaker.
Okay. Thank you.
The next speaker is Roger Moreira from Universidade Federal do Fluminense.
Hello again. My name is Roger Moreira, and I'm here to talk about Benjamin fair instabilities triggered by shear currents. This work is conducted by me from Fluminense Federal University, Rio de Janeiro. also by Júlio Chacaltana from Federal University of Espírito Santo, and also Nelson from Federal University of Rio de Janeiro. It's well known that modulation instabilities were investigated by several authors. I cited some of them here. And we know that depending on the sign and magnitude of the shear flow, vorticity can significantly affect the envelope of these modulated waves. And we are looking actually on these effects. And we had a previous work in which we investigated the vorticity effects on a monochromatic wave train, and could see that these adverse and following shear flows could block and break in case of sufficiently strong flows, and also it can round the wave crests in the case of following shear currents. So here it's the time evolution of wave train. So here it's time, and we can see the waves propagating from the left to the right side over positive shear current. And due to this interaction, we can see here that waves after a certain time begin to have the sharpening crest. And this effect, when compared to the case where no vorticity is applied, I mean, it's easy to see that there is a change here of the wave profile, and also of phase shift that we can find in the wave field. So in the case, for example, of a negative vorticity, we can also see here that a rounded crest, I mean, that can appear, and also difference between the phase of these waves. So based on this, we knew, and I presented this before yesterday, that wave properties are they contribute to, vorticity contributes to change these wave properties, and these changes are significantly different when we have here different magnitudes and also directions of the shear flow. So the main purpose here in this study is to study the effects of these uniform vorticities on BFI. And we started to work on this subject based initially using an experimental work that was published by Ma in 2012. This is a JFM paper in which they've used a flume in China and considered the initial condition in which we got these waves. And here I'm showing the time series of situation here in which we got this bichromatic, the seeded waves, and after a probe that is located afterwards, we can see easily here the formation of BFI. So here is the time series, and here is the spectrum that they showed for different positions of the probes. So we start to investigate it numerically, this problem. So what we did was to construct a seeded initial condition in which we got here the formation. In the case, we extracted several of the experiments from this paper, and we used the SB1 as a reference, and I'm going to show results for this experiment. So the wave steepness is 0.11 in this case, and we've used these perturbations to have the initial condition used in our numerical simulations. The initial value problem is again based on Laplace's equation. Also, we defined here the kinematic and dynamic boundary conditions. The dynamic boundary conditions incorporates here the vorticity and the difference that we have from the experiments that we are considering a periodic domain. So, I mean, for our purpose, of studying the effects of vorticity, we were qualitatively satisfied with this approach. We considered also deep water, and here is the non-dimensionalization. So the solution is based again on a boundary integral method, and in this case we are only looking at the effects of the shear over the propagation of this wave train. So here is the results that we compared to qualitatively with the results of MA 2012, and we can see here that the our condition, seeded initial condition here, evolves from this time series to that one, and here are the spectra that we could find, which were pretty similar with those obtained by the experimental setup by Ma. So we then introduced in our model vorticity, and what we could see here, that in the presence of positive vorticity, for sure that we got BFI still present, and we have here the sign stability being augmented because of the positive shear flow. In the case of negative vorticity, we actually didn't have this. We had this adverse, this following shear flow actually promote the disappearance of the Benjamin fair instability, which was, proposed by several authors that I mentioned before. So we could also see that comparing these two pictures from the spectrum, that there is here also completely different setup, and this is our results that we start to investigate and see that they were in accordance with those papers. So our main conclusions here is that the theoretical results are validated with the experiments, despite the fact that we are using periodic domain. We could see that negative vorticity suppress BFI for waves propagating in the same direction as the currents, but with positive vorticities, we got modulation stability enhanced for waves propagating against these adverse currents. Our next steps here is to study the effects of a falling and stopping, falling current and stopping velocities on BFI, including vorticity. We had a paper published before in which we studied the effects of these following and stopping velocities on a bichromatic wave train, and we could see in that work that the individual components of the bichromatic wave train become almost monochromatic beyond the blocking region, And we hope that, we can introduce also in our model these currents and also vorticity to see what happens to BFI. So this is an idea that we had and we plan to carry afterwards. Okay, so that's it. Thank you very much. Okay.
Questions? Alex?
Roger, it's a very interesting talk and very interesting a problem setup, right? I have many questions to you. I don't want to bother the audience with all of them. Maybe we can talk later. But one, because you introduce vorticity, which in physical sense would be turbulence if it's a random vorticity at the surface, right?
Yes.
And that is the physical setup which is always present, right? Even if in the field your waves are, there's no turbulence, right?
Mm-hmm.
It's generated at the surface by the viscosity, right? That's
Mm-hmm.
Longer-Higgins mechanism.
Mm-hmm.
So it's
Mm-hmm.
always like this, like what you
Yes.
do, right? What Miguel has presented is fully a potential models, right?
Yes.
They don't exist, right? Because at the surface you always have vorticity.
Yes.
So what you presented is valid everywhere, right? In most general case.
Mm-hmm.
Even in Miguel's theories, they have to be introduced if they're important. Now, here's my question, right? You do them with the current. What if the current is zero? Is it still important effect that positive vorticity magnifies the instability and negative suppresses
Sorry,
it?
I couldn't understand the question.
If there is no current,
current? What do you mean?
the current, the water is not moving, right? There is no permanent current, right? Your problem deals with the waves on top of the shear current, right?
Yes. Oh, okay, the current. Okay.
What
okay.
if the current is zero, right?
Mhm.
Do you still have this effect of vorticity on the Benjamin Ferrer instability?
Yeah, the results that I show here, what do you mean if I'm considering the situation in which we don't have vorticity? That's the question, isn't it? So that's the one that I've got here.
But you always
that's the
have
result.
current, right? I'm asking.
No, this one, it doesn't have the current.
But no vorticity either.
No vorticity and no current.
What if there is no current, but there is vorticity?
In this case, I don't have any current. The waves are propagating from the left to the right side and got the probes with these two time series. There's
Okay.
no current here. So
All right.
what we could see is that, the BFI is evolving the same as the same case that it happens to the experimental setup of Ma. Okay.
Yeah. Okay.
What we are planning in the future is to introduce the underlying current and see what happens to BFI. In that case, we simulate this case here. This case there is no current here. That's just that seeded initial condition propagating from the left to the right side. That's it. Okay.
Hi, Roger, very nice talk. And just continue with Alex's questions. Is it possible for you to include vorticity without current, maybe directly from the ocean waves or water waves, whatever?
Yeah,
that's the question. Yeah, yeah.
Okay. What here I'm introducing vorticity to the boundary condition. That's the case of positive vorticity.
Right, but that's depending. That's mainly driven by the currents, right?
Yes, the positive vorticity would induce. I will show, for example, this picture here.
The question is
here.
The question is let's forget about currents, right? Zero currents.
Okay.
Could it be possible to include vorticity generated by the waves and then see what happens.
Yeah, I mean, now I understand. I mean, what I'm here is using potential flow problem. So I'm introducing a constant vorticity to the problem. And the main trouble is, I mean, to find out the magnitude that would represent physically something that's happening. For example, like wind, gust of wind over the free surface. Yeah, we had this discussion with Alex yesterday, and I'm trying to figure out how can we couple, the physical condition of, for example, a gust of wind over the free surface, and estimate the vorticity that we should apply to our model. Okay.
Okay. I remember that there is a paper by Phillips expressing vorticity from waves without current. I'll look for it.
Okay. Okay. Thank you very much.
At the surface, it's longer Higgins mechanism, right?
Yes,
that's a boundary condition, but there is no current.
Yes.
Right? There is vorticity, but no current.
Yes.
Is it possible to do in your model?
Yes, yes. I mean, this vorticity is coming into my boundary condition, so it is introduced there.
This experiment is with current. Can you do the same without current?
What I mean is that, for example, here, I can't find here. The vorticity here is being introduced here. And what we mean is that, I mean, if I can, for example, put like a value of vorticity that is independent of the current.
No, you keep it, just there is no current, right?
Okay.
Over there, the kinematic condition is no current, right?
Okay, I think it's better to discuss this. Okay.
Okay. Another question? Okay, thank you, Roger.
Thank you. Thank you.
So the last speaker of this session is Maura Brunetti from University of Geneva.
This is open. Yes. Okay. So thank you to give me the opportunity to present this work. This is a work that we started in 2019. And now we have published the results in physical review letters. And I want to start by acknowledge my colleagues. So from the University of Geneva, Alexis Gomel, that is our PhD student from Argentina that in principle should have come here at my place, but he's writing the PhD thesis now, so he couldn't come. Andrea Armaroli is now in France, and Jérôme Kasparian from, in our group. And we asked for help in performing the experimental setup to Amin Chapchub that was at the moment in Sydney, and to Stefano Trillo from University of Herrera for interpretation of the results. So the starting idea came from nonlinear optics. As Miguel Honorato said, there are many connections between nonlinear optics and rock waves because both systems can be described by the same equation, the nonlinear Schrödinger equation. So the idea in this paper was that they considered an optical fiber with a changing, with a changing dispersion term. So along the propagation of the fiber, the dispersion change, and they arrived to change the solution that described the system at the beginning. So the Akhmediev breeder here that you recognize here, they succeed in stabilize this solution at the maximal amplitude of the Akhmediev breeder, and in the following propagation length, the solution stayed at the maximal amplitude. So it was like a freezing of the rock wave. So you recognize here the Akhmediev breeder. It is like a respiration cycle. So you start to the expiration phase here until a maximum amplitude, and then the expiration phase toward the initial conditions. So the idea is to reproduce this kind of thing in a water tank. So this was the idea, and to do this, we consider the propagation in bathymetry that is not uniform, because in this case, so we have an equation like this at the main order in steepness. So you have the dispersion term, the nonlinear term, a shoaling term that depends on the bathymetry effect, and of course dissipation. So we with a bathymetry that change in space, you introduce a new degree of freedom. So you can now play with the values of the dispersion and nonlinear term in order to change the solution as you wish. So what we study here is the regime in deep water, so the regime of focusing, and so in this part of this is the nonlinear coefficient that changed this the sign here at this threshold value, and this is the dispersion coefficient. So you see that in the focusing region, the values of the nonlinear coefficient and the dispersion coefficient change a bit. So you can profit of this to obtain a freezing of the rock wave. Let's see how to do in practice. So the first thing is to transform this equation here toward the standard form of the nonlinear Schrödinger equation. So, and this is very simple, as explained in this paper, 78. So you can just change the definition of the envelope, and so you introduce a new envelope that depends also on the shoaling term and the dissipative term. So you end up with a nonlinear Schrödinger equation where the dispersion term is the same as before, but in the nonlinear term you include also the effect of the shoaling and the dissipation. So, and this is important because now that we have a nonlinear Schrödinger equation of this form, we know well which are the solutions, the analytical solutions of these equations. So we can make the transformation between one solution to the other. So the idea is to start so in deep water with an Akhmediev breeder, and then change here the bathymetry, and to end up here with another solution of the nonlinear Schrödinger equation. Of course, the nonlinear Schrödinger equation is just an approximation in a real world, in the sense that it is the the equation that describe the evolution of the envelope at main orders in the steepness. And of course, you have to avoid as much as possible the reflection effect, especially here when the bathymetry change. So the condition that you have to require is that the depth change here should be smaller than the length where the bathymetry change, and should be smaller than the nonlinear length, that is the length of the cycle of the breather. So when you, so this is a condition that you need to respect. So the idea is that we start with this solution, and at the maximum, at the position where the breather is maximal. So we consider this section, this vertical section here, and the amplitude of the envelope as this form. So at this position, we change the bathymetry so that the solution change to another type of solution that is, in this case, the dinoidal solution. So a solution that is periodic in time, but is constant in amplitude. So it's stationary solution of the nonlinear Schrödinger equation. And the cross-section of this solution has this form. So if you superpose the two forms, you see that you can find the parameter where they are very close each other. And also, if you perform a Fourier transform at this position, at this cross-section, you see that the spectrum can be really similar. So in red is the dinoidal spectrum, and in blue the Archimedean. And so you can find the right parameters. You can set up the bathymetry in such a way that parameters correspond in this way. So before showing you the experimental results that we did, showing that this is indeed possible, I want you to show you another way to interpret this kind of change between one solution to the other. And for this, we consider a simplified model. So just 3 waves, the carrier one and 2 sidebands. And in this case, it is very useful because this kind of simple model, because you can define 2 canonical variables. So the conversion rate to sidebands, so that is the ratio between the amplitude square of the 2 sidebands divided by the energy of the system, and the relative phase of the sideband with respect to the carrier. So with introducing these 2 canonical variables, you can show that this is you can find the Hamiltonian of this system that is written here. And you see that the Hamiltonian depends, okay, on the 2 canonical variables, but also on this parameter gamma that allow you to change the structure of the phase space. So here it is represented the Hamiltonian as a function of the 2 canonical variables, and you see that so the Hamiltonian is negative inside this separatrix, and the separatrix correspond in the real model to the Archimedean breather. And so inside the separatrix there are 2 centers that in the real problem correspond to the dinoidal solution. So the idea is to manipulate the phase space, this phase space here that you see here, so that a point on the separatrix end up to a dnodal, so to a center, by changing this parameter gamma. That depends on the modulation here, the modulation of the sideband. Okay, so this is what happens. So if you start with a point on the separatrix here, and you change the parameter gamma, the Miltonian change consequently, and this initial point that at the beginning was near the separatrix end up into the center. So you transform the Akhmediev brother to a dnodal. And so this is what happens in this simple video. And you can find conditions where the gamma at the beginning is equal to the gamma at the end through the relation between the tuning of the dnodal and the Akhmediev brother. So this is the simple thing that we have tested in a water tank. So this is an example of things that you can do in a water tank with and with the help of Amin, we performed the experiment in Sydney with this water tank with this kind of characteristics, a certain number of wave gauge here, and an artificial floor setup that where the bathymetry has been changed so that this relation is respected. So with this, these are the experimental results. So you see in blue the case with the step, the bathymetry step here. So these are the order of magnitude that we considered, and in red the case without the step. So you see that at the moment where there is the bathymetry change, there is the maximum of the Akhmediev breather. So without a step, you see really the fact that there is a maximum of amplitude, and then the cycle of the breather that goes back to the initial condition. While when there is the step, you have the maximum of the Akhmediev breather, but then it stays constant later on the amplitude. So we have freezed the rock wave, in a sense. So, and this you can also see from extracting the different modes in the wave signal. So you see here in black. So yes, in black, the carrier mode, and in yellow, in particular, the first sideband. So in this column there are the experiment, and here are the numerical simulations. And with step, so the carrier go down and then stabilize, while without a step, the carrier go down at the maximum of the Akhmediev breather respiration cycle, and then go back to the initial position. And the same you can see in the phase behavior, in the sense that when with a step you end up into the center, so the phase stay constant when you end up to the center, while without a step you are on the separatrix, so the phase continue to increase. And we have confirmed the result with the numerical simulations. Okay, there are and another thing to observe is that if you consider the second order sidebands, you see that they are very, very small, so 6% of the carrier So this means that the three-wave approximation is very, very good in this case. So another way to plot is using the three-wave model. So in red, you see that so without a step, you follow the separatrix, more or less like this. And while with a step, you end up into the center, if you remember this plot in the phase space. Another way is to estimate the contrast. So when the Archimedes brother make the respiration cycle, it goes back to, oops, no, sorry. It goes back to the initial position in red, while in the other case, it stays constant. So these are ways that you can use to measure the fact that you have changed indeed the solution. So to conclude, we have performed this experiment, and we have seen that the nonlinear Schrödinger equation framework is sufficient in this case, even if, of course, in the water tank there is a lot of dissipation and high-order terms cannot, in general, be neglected. But in this setup, we have succeeded in controlling all these effects. So, and indeed, we have seen that, and also the setup has been chosen so that the reflections are minimized. So in this case, we can use, it was possible to use the NLS framework. And indeed, we have shown that if you change the parameter in the equation, so in this case, the bathymetry change in space along the evolution of the wave, you can stabilize the solution toward the solution that you want. So in this case, we have stabilized the Archimedes brother at the maximum amplitude. So this is a very general, interesting theoretical way to stabilize a solution that can have many other applications, other fields. And of course, at the end, as in the case of the optical experiment, there are residual oscillations in the amplitude, and these are due to the fact that the matching between the two solutions is not perfect. So we are working to make this matching even better, but this is not okay. This is a possible future work, but another thing that we have noted, observed during the experiments is that when you change the experiment was done in deep water regime. If you change toward intermediate waters, so in principle you have a larger change of the dispersion coefficient and the linear coefficient. So in principle is interesting regime, but in this case the mean flow has a larger effect, and so we are preparing now a paper on the role of the mean flow in this case. Okay, thank you very much.
Thank you, Maura. Questions? Frederick?
Thank you. Just by curiosity, if then you have the slope that goes down, and then if you were putting it back, then would you go back to the
Archimedes?
Yes.
the shift from the dinodal to the Archimedean. Yes, in principle you can also. So this show that the bathymetry effect can really change one solution to the other. So we should take into account this. Yeah, in principle, yes.
Yeah. And then, of course, there is the fact that, there is a little bit of dissipation. So then you are not exactly.
Yeah, in the experiment, it's really difficult to realize something like this because, in this case, we had a water tank where we were able to study just one cycle of the breather, because otherwise, if you go longer, dissipation dominates, and in this case, you end up to another
we did, but without the experiments, we did this with the KdV equation and this kind of transitions, and so.
Yeah.
Thank you.
Any other questions? So we can go for a coffee and start the final session at 5.
Hello, please. Come on. Shall we get started? Hello. Hello, colleagues. Please, let's get started. The next speaker needs no introduction, right? He has a very large, impressive production. And please, let's welcome Luigi Cavalieri.
Thank you to everyone. First of all, thanks for organizing this meeting. It's all interesting to see a different perspective, different environment. The meeting, LatWave 22, at last, after 2 years that we've been waiting for. And when I was asked to give a talk, I had no clear idea of the local environment, and there is more coastal engineering than I expected. My comment will be about wind wave modeling. It will be very critical for my own work. And the question is that what we are doing today and what we... Okay, let's start with the positive aspect. This is a comparison between ECMWF wind speed and the one measured from satellite. Couldn't be better. It is the bias, well, you can read, the bias is the order of 10 centimeters per second. And the slope is 995. So the question is, it's very hard to do any better. This is for the wave height, and this is for the comparison with buoy. So what can we do better than this? We have plenty of global reanalysis, the one you can see there. And ERA 5 is the most used one. You have 70 years of data, 30 kilometer resolution, full hourly spectra, two-dimensional spectra for 70 years on the whole globe. And they're already talking about ERA 6. I don't know the resolution. And we are submerged with satellite data. This is a Sentinel-6. And this is the French-Chinese satellite. I don't know how many of you are dealing with this satellite, but one of my criticisms that I will do now in a minute is that this satellite shoot down such a tremendous amount of data that we have no time for dealing with them, especially if you are a user or a wave modeler. I mean, people deal with this satellite data. We are talking at the order of 1 terabyte per day. So the question is how you store this data. And people actually use this satellite just to justify the Chinese-French series of paper. But it is we are submerged by that. That's one of my criticisms. This is the amount of buoy that we have to deal with. And there are various sources, but a very common source is this one. And this was the first one, was a very light buoy, 30 centimeter diameter, $5,000. And this is a small, can you see all the pump? All these buoys that are sparse around. What they are doing, and also Scripps is doing the same, is that they are putting 100 of this buoy floating freely on the ocean, and they drift away, and they give you current, of course, with GPS, and two-dimensional spectra. And all this is assimilated also by, of course, the global model. And you can imagine which the volume data you have to deal with, and how many wave forecasts we have in the world. Just a global one. I have no idea how many have been done, but wave forecast, yes. And we mentioned Germany, England, ECMWF, Australia, US, China, I'm sure, and probably I'm forgetting someone. And then we have literally 100 of local one, of course, as we do, for instance, with Luciana, that we have the Mediterranean, the Adriatic, and these sort of things. Okay, and then to conclude the positive side, we have a fantastic high-resolution experiment. This one by Yulia Troitskaya, like this. This is an experiment in her wave channel. But to give you idea, you are looking at something that is of the order of micron. So that is the order of magnitude. You're talking about microsecond to do this sort of things. And this is a very important, that's what she called sail. And actually how is a sort of a spray in the atmosphere. And that's what I will end up with. And various processes, then this is the first, the sail, and then this sail breaks. And here it breaks larger droplets on the side, and the small one. And I asked Alex Soloviev, we will see in a short while, a beautiful presentation that he passed to me by, and if he can reproduce this, but the computer power is not yet enough. And the big question that we have to solve is to apply this to in practical application, because we are talking about processes that are the order of micron, and we have to then to apply this to a model that has a 10-kilometer resolution. And sea surface tropical cycle condition. How many of you have seen those beautiful video first in a lifetime taken in the middle of a hurricane with a sailing boat, automatic sailing boat, and 10, 15 meter high, and it goes by itself in the middle. There is an incredible video. If you've never done, look on the internet, try to find it. It's really unbelievable. It's the first evidence, documented evidence of what is going on in a hurricane or a typhoon or a cyclone you want to call. And this is an image from that I was given by Alex, but we will have the video later on that show you what an idea. Alex, is this realistic or is it idealization?
Idealistic, but it's actually a computation of fluid dynamics, and it involves both water, air, interface with certain tension. So in that sense, it's realistic, but of course it's in small domain.
But this is the best that we can guess of what we have at the moment, of course.
Yeah, probably, yes.
The point. Okay, everything okay. Couldn't be better, so we can go everything for dinner tonight and be happy. We have done everything, no problem. But, I'm tapping myself on the shoulder. Let's look from a different perspective, okay? What you see here, I'm an old man, of course, by far the oldest one in the audience. And this is the history or the story of the main discovery and happening in wave theory. Everything, perhaps I'm repeating something obvious for the young people, but everything started in 1942, during the Second World War. Someone went to Scripps and asked to them to produce a waveforecast model. And then Walter Monk was a student, and he was to make a wave for, a table, given the wind, fetch, and duration. This is a wave height. Just to give you an idea, this was still used until 1980, 1990 by engineers, coastal engineers. In any case, in 52, Wheeler, Pearson, and Wilbur Marks came out with the idea of the spectrum. There is an interesting story. Pearson was famous for this. They became, however, the credit go to Marks, to Wilbur. Wilbur was an optician, and during a beer in the evening, they say, Willard, why don't you apply Fourier thesis, this Fourier series to your waves? The day after, Wilbur was killed in a car accident. But the idea was left, and Willard published the paper, the name of both of them, and then that was in start. Then followed, a few years later, the first attempt wave modeling in France by GLC. Klaus Hasselmann came out a few years later with a nonlinear interaction. Johnson experiment in the 70s. The Swamp book, Swamp intercomparison study in 80. Luciana and I took part. Then in 86 was a one model. A few years later, Wave Watch. And then the last big breakthrough was a theoretical big true was Peter Janssen in 91 with the air-sea coupling. That when the oceanographers were welcomed at last by meteorologists because Peter Janssen showed that taking waves into account was improving the meteorological forecast. Then, of course, the one book in 94. And then, let's say 20 years ago, we had Alex, who is reading something else. No, come on, carry on, I don't mind. But I'm talking about you, about Lake George. We have a different opinion with him about this. I think you and Young and Mark did the best, by far the best that could be done. Fantastic experiment. My point is that is still a theory about 15 centimeter wave height. And of course, how much accepted is ST6 now, Sasha?
Every global model, a Waywatch 3 and WARM and S1, and at least Australian Bureau of Meteorology is using
now,
ST6.
most of people still use ST4, I believe. I mean, at least what I see around.
That's fine. But Luigi, the gravity waves, they scale, right? 50 centimeters.
No,
right?
I fully agree.
It's away from capillary waves, and then they scale.
I'm highly critical that we'll see about ST4 or WARM or these sort of things, you know. But in any case. Anyhow, the question is, what have we done, done in the last 20 years? Lot of measurements, buoy and platform, satellite. Each satellite shot down 1 terabyte per day. Lab experiment, wave flume, basin with without wind, small scale process, Yulia Troitskaya, that I mentioned, video stereo system. Here we go. This is the oceanographic tower that we have offshore Venice, 16 kilometers off the coast, 16-meter depths. And this is the work of Alvise Benetazzo, who is a young colleague of mine. And this is a three-dimensional reconstruction of the surface. This is the original video with the color is the color. This is an incredible system because you cover a 60 by 60 meter and side, and with basically a wave gauge like 20 centimeter, which means you have the order of practically 100,000 wave gauge there measuring. And you derive everything about this. Theory. Hell, we don't have theory. The only group, as far as I know, that make a basic theory is Zakharov et al., but no, there is no application. I've discussed it with Vladimir many times, and they are theoretician, and I've never been able to apply what to say. Not to me, not to everyone. We have, of course, a theory of extreme waves. We have seen something also today, and lots of computer simulation. That most people do. No, even my younger colleague in the office, they have the model of the Mediterranean model, the model of the Mediterranean Sea. You change a couple of parameters, press a button, go. 3 weeks of computer simulation, another terabyte of data, and these sort of things. I put this a question first, so you can make your guess. How is the wave community splitting its time? How much? Theory, laboratory, computer, this sort of thing. Make your guess. This is mine. 80% is computer simulation, 15% satellite data, 4% lab. I'm very generous to put 1% theory. I think it is much less, 0.1. Oh. Sorry? No, sorry, I couldn't hear you.
In situ observations, the buoys and everything, right?
Okay.
That should be, some percentage is there, right? I agree it's small, but it's important.
Okay. Well, let's make discussion, because that's the interesting part. We are submerged by data. And there are people who claim artificial intelligence, big data, claiming that we can forget the theory and models, go ahead with only data. Of course, there is a contradiction of terms in this, but forget it for the time being. We have so many data that ECMWF assimilate only 10% of the data. So, which new subject shall we focus on the next year? Is the field exhausted? I mean, after all, you can saturate most of them. We are asymptotic. Of course, we can always carve out a little corner. Of course, I'm not denying, of course, we need what we have seen in these days, coastal engineering. Because if you have to build a harbor, there is no discussion. You have to evaluate waves in that area, in those conditions, and blah, blah. So plenty of work. But I'm talking about a basic, really, approach to the theory, to the basic way. Where are the new theory? What shall we work on? This is how I think we should face the problem. Besides, are we fully satisfied with the present theory? I try to be, do we believe this is the right only path? I always try to be very critical with myself. Arguing, I never pat on my shoulder and say, how good, no, I mean, always try it. For instance, are we assume that spectral approach is a definitive solution? Fantastic tool, of course. It led us to where we are. Thank you to Joseph Fourier. By the way, do you know why Fourier invented the spectral analysis? Certainly not for waves. That was an idea of Marx. He had to solve the heat transfer in a wall, on the corner of a wall. He invented the new mathematics just to solve the problem. This kind of people. Okay, but the question is, I believe a spectral approach is fantastic, is beautiful, fantastic, useful, but it's not the only solution. Miguel today and Maura also gave an idea of the determinism, actually. That's why I asked to Miguel the question. Suppose that you know the sea surface determination for 1 kilometer. Can you actually foresee the freak wave coming. I don't know. I don't have a solution. But the processes that we represent in input, they are input by wind. I will close my lecture with the image and let you think about, apart from the one we have already seen. Why does a strong rain stop input by wind? Oil is the same. According to theory, it should not be like that. I spent about 1 year of my life measuring waves on an oceanographic tower in the middle of the storm. It was beautiful. I learned a lot. But do we really believe, when you see a stormy sea, breaking wave, that you can split this into different sinusoidal components where the wind make a nice logarithmic profile, and you can make the input to that spectral component independently of what is going on? No, I don't think this is the truth. It works. Fantastic. My background is mechanical engineer, so I always look at the practical problem, but I don't believe to that. White capping. Most formulations simply ignore wind effect. Only Alex, I think, took wind into account, right? For instance, most of the formulation, like ST4 or WOM, take the spectrum and evaluate white capping. Rubbish. If there is no wind, there is no white capping. I've seen this physically. Let's go to some constructive conclusion. Where should we work in the next 20 years? I strongly believe that the key factor where to work on as a humanity and everything, Earth interaction. People, I discussing this with meteorologists, they want to ignore. But when you have a climate model where the Earth interaction, most of the time, are parameterized as alpha U square. I mean, we are still in prehistory. And when you have a storm, Earth interaction or contact surface is increased of 1 or 2 orders of magnitude, which means that 20% of the ocean that here or there, somewhere, is permanently in stormy condition, is actually controlling through wave breaking most of the air-sea exchange in the world. And this is a subject where I think we should work on. Wave modeling needed to be sorted out. Climate modeling. Ocean atmosphere parameterized in very primitive wave. Wave artifact. Okay, the last sentence is just what I just already told you. And we have a beautiful work in this direction. The lab experiment by Yulia Troyskaya, the computer simulation by Alex, and the first class work by Luke Deike. Now the task is to go further in this direction. Remember, this is beginning. We are always the beginning of our climbing. And the point is to summarize of this micro finding into workable formula for large-scale application. And that is the next step, of course, of the problem. But don't draw back from the problem. It's very easy to do again what you can do each other, perhaps with your friend in the evening, pat each other's shoulder, how good we are, and blah, blah. You have to solve the problem, because that's what has been done in the past. Again, this is Julia. And this is a fantastic simulation by Alex. It's unbelievable. You should describe it if you want. Just have a look. This is a faint idea of what is going on in practice, every breakers. And what is the simulation of the hurricane? This one. Yeah. Mm-hmm. In any case, 6 minutes to go, so we have seen enough of this.
Yeah, and it's realistic in that sense that spray generated in natural way at their interface. We are not ejecting it; it's just produced by itself. And also, what is interesting about this model, actually, it's all kind of taken from engineering computational fluid dynamics, because they're using this, calling this process automation, and they are far ahead of RC interaction. We are still kind of trying to trail that. This type of model is able to produce C-spray generation function, but for the first time probably it's real, because it's showing what is going on really at the interface, because other methods include measurements somewhere above wave crest and then using some assumptions. They sometimes don't work in order to produce that function, but this producing it directly. We were so amazed when found it in that computational engineering that decided to apply it.
Okay, we have seen this. This is my last recommendation. And do not repeat, thanks to computer, what you know already how to do. This is a research. There is a little joke about the research, if you want. There are two professors in England, John and Peter. And John asked to Peter, Peter, it's terrible. It's terrible. You know, people are doing it again and again and again the same things. And Peter tells to John, John, this is why it's not called search, but research. Basically, it is true. And of course, thank you for listening. I much appreciate your comment, not only now, but even for email, shout to me. And this is a last picture I meant to show to you. And this is something that with Luciana we found internet many years ago, and some of you have already seen this slide, of course. I let the other people guess what is absolutely unusual, strange, and indicative in this photo. It's not our photo. We found on internet, we found the author was in the Philippines or something like that, you know, the Pacific somewhere. But it's fantastic. It tells you a lot if you know how to look at. Okay, thanks a lot. And if you want to throw tomato or whatever you want, you're free. Thanks.
Thank you, Luigi. We have time for questions.
We already discussed. Oh, Jesus.
Jesus.
Well, let it there for a moment, and then we explain what is.
Thanks, Gigi. Very shaky. And I have a question that will sound heretical. So I'm trying to think how to formulate it, because it's related to what you have been mentioning and also what Alex mentioned in his talk. And it's the fact that somehow we as a community, we ourselves develop paradigms in the methods that we use and everything. It's like when I started working in waves like 20 years ago, it was very difficult for me to understand nonlinear interactions. Until some years later, I managed to understand. I saw computer simulations and everything, but I never actually believed in nonlinear interactions as how the Hasselmann equations are described. And Alex just mentioned that, okay, we measure everything except nonlinear interactions, because we assume and we take for granted that is correct. I still struggle now to understand how nonlinear interaction works.
Thank you.
And I don't think they work correctly.
Look,
but this is the kind of things that.
Look.
But one more thing. One related to that is the fact that you mentioned that the weather centers, they keep increasing resolution and these sort of things. And like, again, 20 years ago, they were talking about, okay, we don't have computer power to put exact nonlinear interactions.
Rubbish. rubbish, because as soon as they have the computer power, they double the resolution, and we are back to the same problem. And in any case, thank you for this, because I always say that I will be happy to die. I'm not a theoretician. I will be happy to die when someone explains in physical terms what is nonlinear interaction. In any case, going to this one.
Thank you, Gigi.
As soon as I've seen this, there are two characteristics in this picture. First of all, this is a wind sea. It's not a swell. You see immediately from the steepness of the wave irregularity, but there is not a single breaker. It's a very windy condition. Very windy condition. A wind sea without a breaker. The reason that we work out is that the rain kills the very short waves where the roughness lies, most of it, as the wind is slicing over the wave without actually friction on the waves. That is the effect of rain. Indeed, working at CMWF with Luciana, we work out that when it is raining, the ECMWF model is overestimating the wave height because they keep inputting energy, but because it is raining, when it is raining hard, by the way, not like this morning, of course, absolutely the sea is smooth. Fred, you mentioned that you are working on the subject. Yeah. I'm glad, because it's something, because people do not have a solution, they like to ignore a problem. That is typical. On the contrary, that's what makes life interesting. Of course, all the young people need to publish, because on the contrary, don't make a career. So you have to work. So devote 50% of your time to running model and publishing paper or whatever journal you find. But try to devote a part of your time also to this. We need that. We need blood. We want to be easy. One out of you will succeed. But that will be worthwhile. It's an investment. That's where we have to work. When we're looking for a new way in the mountain or in the forest, we don't know. We have to try this way, this way, this way, this way. We don't know where a solution is. There are smart people who can see far ahead. Okay, they are Hasselmann. Nobel. By the way, Hasselmann, the one who invented nonlinear interaction, is the one who got the Nobel Prize 1 year ago. Not for the nonlinear interaction. Because for him, waves were just a side subject. Oh, I find many times, let me write something. He solved the problem of the climate, showing by nonlinear interaction that the high frequency component of the climate can change the long-term derivations of the low frequency climate. Yes, quite interesting. Any case, thanks for everything.
Questions? Somebody else? So, Luigi, thank you very much.
This one? Oh. What Klaus did, I can pass to you the paper if you want. It's an extremely difficult paper. I can look through and read the introduction and the conclusion, That is already enough for me. Now, there is a general idea that the high frequency are filtered out. A long-term climate is actually what is dominating. Actually, Klaus showed that the high frequency can actually affect, trying some tipping point, the long-term behavior of the climate. Okay. Thank you very much.
Thank you very much, Luigi. Our next speaker is Paula Espinosa. Paula, por favor. You can point here, right? Straight away, so you can face the audience, right? So you can press and move. This is to move back and forth. In the middle one, you can, so you can face the audience, right?
Hello, everybody. My name is Paula. I am a master studying at National University of Colombia. Today, I'll tell you about this small study entitled "Quantification of Wave Dissipation on a Coral Reef." The case study in San Andrés Island, Colombia, with my advisors, Professor Andrés Osorio and Professor Juan David Osorio. San Andrés Island is located at northeast of the country in the Caribbean Sea and is the most densest island in the country, and is characterized by there are many marine ecosystems in the zone, like corals, algae, mangroves, and seagrasses. The island have a challenge for example, a lake of a baseline for increased drinking water coverage through sustainable methods like desalination plants, management of environment impacts, mainly in this marine ecosystem, like little scientific support for the ecosystem service, and to take action for combat the climate change. The study zone is northeast of the island. In this zone, where the pressure sensor, four pressure sensors were deployed. In this zone, outside the barrier reef, and this in a little reef. These sensors were deployed to 10 meters and 5 meters, and in the near the shore, the coasts, 4.6 meters and 1.4 meters. With this data, we use the numerical model SWAM, as some speakers explain this equation. The left side explain the cinematic part of the evolution of action density balance, and the right side explain the physical process. Into physical process, we focus in this equation that represent the bottom friction dissipation, and we focus in this bottom frictional coefficient. The model considered this formulation for found this coefficient, and we try to see what is the best. For the island, is important that model with this precision of this coefficient, because these have important effects on a reef ecosystem as a modulating substrate type and venting community structure and morphology. For the model, we fix bathymetry from JEPCO and bathymetric charts, the wave boundary in the red points from ERA5, and wind grid in yellow points. And for mesh, we made a nesting of the grid to reach the study zone with a resolution of 15 meters. For the calibration and validation, we use this formulation for the friction coefficient, and I found that in this time, this data was deployed during November or 2019 and 2020. With this data, we found that the model underestimated these waves, these significant waves, and in general, trends the time series. We established 4 scenarios considering sea level rise that represent the bottom is 1 meter deepest, and considering wave condition parameters in mean condition and extreme condition, and bottom condition for smooth and rough condition. We take a value of what friction coefficient is the best for a coral reef environment or system. We take from the literature different values for this work of project was in Palmyra Atoll in Hawaii. He said that the zone is high frictional environment. For model to sand or smoke condition, we take TB. What we say, he said that the low roughness condition, and the typical value is used of the lower for a substrate for a coverage in a coral zone. And in the smooth condition, with a significant wave height of 0.66 meters, reduced to 50%, and for roughness condition, this reduced to 70%. And in the condition extreme, it is very similar. And for considering sea level rise with a meteor, it's important for the roughness condition. It's the most. It represents that the coral reef in this zone are important for dissipation in the coast, and these channels were without corals are the most important for coming wave and flood this zone. Now we evaluate the average rate of frictional dissipation wave outside the barrier. Considering this data, with the purpose of this is this question: how is the bottom friction model, where this data and the model proposed by Rogers in wave dynamic of Palmyra Atoll, we found the frictional coefficient for the San Andres Island, and we found that this formulation what used in SWAN is for for different conditions, and San Andres have other conditions. So it's a work and is open to more investigation. And other studies related with this is evaluate the transformation process with the currents in a reef environment, and establish scenarios under extreme conditions like Hurricane Pass, because San Andres is very exposed to this extreme condition. Yeah.
Have time for questions?
Paula, I could not read the formula that you put at the end for bottom friction. Which one do you use? Yeah, I cannot. No, the next one. Yeah, I cannot read the formula that you use. The general point, maybe you use the right one, but most of the model are completely wrong theory about bottom friction. So the reason is very simple. Bottom friction is not important. Breaking on the coast is much more important, so it does matter. But most of the model go with the Johnson formula, which is rubbish. Okay. I'm sorry for the Klaus Wasserman Nobel Prize.
But it's important for this zone that is a lagoon. There are many marine ecosystems, and in this zone, in the barrier, the breaking wave is the most important.
Yes,
really. But this zone is not the objective of this work is know this environment affected by the hydrodynamic.
Okay. But in any case, if you want to do something better, there are ways. Okay. Thank you.
Okay.
Nice presentation. Thank you. I wonder how the hydrodynamics were considered in your model.
This is only waves.
Yeah. So because you mentioned that there's a pool there in a lagoon. How do you consider vorticity and maybe
this is my
launch or rotational? Because that place seems to be very shallow, isn't it?
Yes.
So maybe the wave stress or maybe the wave energy flux depends of these gyres, isn't it? So are you planning to complement these results with hydrodynamic coupling? And later, have you considered to the temperature rise because ecosystems every day are weaker, yeah? So this bottom friction is lower every day. So how are you planning doing that?
We now in my master study we coupled DELF and SWAM. The idea is relate the currents with the wave and how this hydrodynamic affect this zone specifically.
Okay, is anyone studying the temperature rise and its effects over the biomass of the bottom friction there?
Yes, the purpose of the study is that evaluate the change in salinity and temperature. what is the effect on this environment.
But
The Delft is modulated with temperature and salinity conditions.
Thank you.
Thank you. Thank you, Paula. I'd like to invite the next speaker, Christian Valladares. Hope I've pronounced it correctly. Christian, please. Christian, please. Okay, so move forward, backward, and use the pointer. Okay. So I can point here, so I can paste the audience. Right? Okay. Thank you, Christian.
Okay. Thank you very much. So my name is Christian Valladares. This afternoon, I'm going to talk about wave model evaluation at the spectral level. We are working on this topic with Jesus Portilla and with the valuable comments from Eric Rogers also. So we move on. I'm going to go directly to the problem. We all know that when we need to compare model results versus observations, we use integral parameters like significant height, mean period, mean direction. But in general, wave conditions involve multimodal wave systems. As we know, each component with different characteristics. So in these cases, integral parameters become relatively meaningless because significant height errors tend to cancel each other. So in the wave model reports, we see that, for example, in this picture, that we have a very good fit between model and observation data. But mean period errors tends to get exaggerated, and we have not a very good fit in the case of mean period. So therefore, modelers don't like to show their mean period results. Also, mean direction errors are very inconsistent. So in this slide, we propose the solution to go back to the spectra, and because we have detailed information of individual wave systems that we can identify and treat separately using spectral partitioning. So this example is very illustrative because we have two complete different wave spectra, and with this wind wave going in northeast direction. In the other spectrum, the wind wave is going to southeast direction. The swells are also significantly different, but the integral parameters are very similar. So you can see that wave height is very similar, and with 5.65 in this case and 6 meters in this case. Also, mean period are very similar, and mean directions don't represent the two wave system that we see in the whole spectrum. So we need to be smarter and follow for a better solution. So a previous approach, because we cannot compare direct spectrum by the spectrum, the wave systems, because these wave systems don't start frequently in observed and model data at the same time at the exact same time and don't finish at the exact same time. So a previous approach was to use spectral statistics. These spectral statistics consist in take a selected period of time and to represent the systems in model and buoy, in model and buoy data to identify identify these wave systems in a long term, so we can separate them and compare accordingly. So we can see that this system here, for example, the wave system A, and in long-term wave statistics, we can compare with this A, and the same thing for the other long-term wave systems. But this is not the best solution, or only works when we have well-defined well systems. So in this same case, we can see that these two swell events appears here, but in the long term, but in the buoy in the buoy statistics, we cannot identify very well these two. So we need a more general approach. So this is the comparison of the three long-term wave systems that we see in this slide. So we can see that the wave height comparison is have a very good fit, and but identifying the wave system in a separate way, we don't have this this good fit for each wave system. So in green and blue and red. So we can see that significant height errors tends to cancel each other, and in the case of the mean period, the errors tends to exaggerate in the comparison. So overall integral wave parameters give a distorted picture of the real situation. Okay, so the challenges that we need to solve is that we need to follow the evolution of partitions or wave systems in time to obtain coherent time events. This is not straightforward because of the natural variability of spectral energy. So in this case, we have three spectra at time step t plus 1 and time step t plus 2. And as we can see, the number of partitions identified in each time step is not consistent. So we have 4 partitions in this time step. In the next time step, these 4 partitions becomes 2 partitions. And in the next time step, again appears the 4 partitions, because the observed data is a change. The energy may vary significantly from one time step to another. So we need to use a parameter to compare these partitions. For that, we use spectral correlations. This term have been proved to be a very good way to compare partitions in the 2D wave spectrum. So in this case, we have the spectral correlation formula here, and ET is the 2D wave spectrum of partition I at time t, and ET plus 1 is the 2D wave spectrum of partition J at time t plus 1. In short words, we are identifying the wave system, the matrix of the wave system, and we are becoming this matrix a simple vector, and we are comparing with a simple correlation. It's only that beam per beam, we are making a simple correlation between the wave systems. So in this picture, we can see the results of using this parameter when we compare with correlations is the wave system 1 with wave system 1, we have a correlation of 0.9, and for the other systems, we have a negative correlations. This means that they are not well correlated, and so we know that this is not the same system in the next time step. This is the simple case because we can identify easily with the parameter with what systems are correlated. But this is not the end of the story, because in the example shown before, we have a different number of partitions that we need to correlate. So some partitions combined produce better comparison parameters than if not combined. So in addition, if partitions are not properly combined, they become leftovers. They have a erratic signal. So we need to compare not only partitions, but also their possible correlations. So in this case, we can see that at time step t, we have 4 wave systems. And the time step t plus 1, we have 2 wave systems. And when we compare wave system 1 in green with wave system 1 in green, we have a correlation of 0.62. And when we compare this wave system 2 with wave system 1, we have a correlation of 0.57. So, but if we combine these 2 partitions and we compare with the correlation parameter with the green partition, we have a correlation of 0.45. So the result suggests that before we correlate a wave system, we need to combine the wave system, and then we need to make a link between the 2 of them. This is the same case that I showed before. And we have 2 different spectra, and we have two partitions at this time step, and in the next time step we have more partitions. So the combination here needs to be done in this time step. So partition 1 in green with partition 2 in blue need to be combined to get a better correlation parameter. So the proposed scheme to identify these wave events is to make a correlation between all of wave systems at time step t with all of wave system and at time step t plus 1. So for every time step, we compare partitions via the correlation and all possible pair combinations. So this is the simple part of the algorithm. We compare single wave systems, but we compare also all the individual wave systems with all possible combinations. So we compare this wave system with this combination, and the rest is the same. No? So we compare the rest of the wave systems with all possible combinations at this time step. So in the left we have time step t, and in the right we have time step t plus 1, and also we have combinations in the other side at time step t, and individual systems at time step t plus 1, and also we have all possible combinations between the two time steps. So we need to compare all possible combinations of wave systems to find the best combinations and to give the best possible correlations also. So combinations are not restricted to pairs because the processing is recurrent. So we first we do this step, and then we do in a next step we process again until and in the next iterations to find another possible combinations that gives us a better correlation parameter. So that is the proposed scheme. Okay, and in order to build a robust scheme in this algorithm, we need to know what are the best possible correlations without doubt. And so for this step, we need to make a histogram of the all possible correlations. So in this histogram, you can see that we have the correlations of all wave systems in a period of time. So we select the best possible correlations in this case, okay, and we find a threshold. We select all the possible the best combinations that are over the threshold. But these wave systems have to be the best combinations, not only for individual wave systems but also for the combinations. So single partitions to be connected should not have better correlation if they are alone. So we choose this in this histogram, but in the combination histogram they need to have lower correlation because this means that we don't have ambiguity in the link between the two time steps. So this process is repeated, lowering the correlation threshold with each iteration until no further connections are possible in time series. Okay, so we have some preliminary results. We have the time series here. When we compare directly the wave systems, we have this erratic signal. So we cannot identify very well the wave events. So in this case, we have here in the black line the total energy of the spectra in time. So and the color lines are the wave systems, the individual wave systems that are trying to connect. But as we can see, this signal is very erratic. So we cannot connect. We cannot identify very well the wave systems. So what is the objective? The objective is to get something like this. In the time series, we can identify wave system, separate each other, and identify, for example, what wave systems are appearing in this time series. So this part is very important because, as we can see, we can identify two wave systems that are happening at the same time. So we have this wave system, wave event in red that is developing as we can see, increasing its energy and decreasing their energy. And also at the same time, we have another wave system that can be identified and then obviously compare. Okay, so for our further work, this is done to make a cross-assignment of events. So this approach is based on matching wave events in the two sources detected in the 2D wave spectra. This is an example of data. So, for example, we have in red line the model data, and in blue line the buoy data. So some challenges when we make the cross-assignment of events are that the events do not have the same duration. Start and finish times in each source, model, and observations are not the same. So this is a very important challenge, because we cannot compare the buoy data directly from with the model data. When we identify the events, we can make this easier, but it is current a challenge, because as we see in this part, the events don't start at the same time, and in this part, the events don't finish at the same time. So another thing that may happen when we do the cross-assignment is that the model data can show an event that it doesn't appear in the buoy data. So we need to identify these situations and make some evaluations to do the cross-assignment. So that is it. Thank you for your attention.
Questions?
Thank you. Beautiful job. I see a lot of use in your work, especially when you talk about modeling to solve short scale and try to improve that and find weakness in the model.
Okay.
So I find it's very useful. I have a more technical question for you. So when you do the partitioning of your spectrum, so usually when you do partitioning from buoys, the spectrum is quite rough, so you find many partitions sometimes. And when you do the partition in the modeling, as the spectrum is more smooth, you find sometimes less partitions. So, for example, if you find like 3 partitions in your buoy data and 2 partitions in your model data, how you deal with that?
So that is the thing in my presentation. So yes, that was a problem developing this algorithm, because for example, in this case, as you can see, as you already say, the partitioning is very consistent. So in the 2 time steps, the number of partition agrees, but in model data, this is the common challenge and that we can see. So for that reason, we need to do these combinations, because we make the correlations between wave systems at one time step with the next time step to identify these events. So I don't know if I answered your question. When we have these events in time, we can compare easily the two data. So it's easier to compare the wave system when we can identify in the 2 sources of data. But if we don't have this tool, we are comparing step by step. So that is the challenge. So so that is why we developed this algorithm.
Thank you. It's really useful.
Okay, thank you.
have time for one more question. Jesus?
More than a question, a comment for Pedro. Actually, the thing is that when we want to compare modeling and observations, we go to integral parameters and we ignore everything that's complicated. We just mess up everything and we compare, and we are happy with that. But we have a spectra, so we can do better than that. We can go in more detail, but there is a price, because then you start dealing with many problems. And one of the problems is the one that you mentioned, that sometimes partitions appear in the model but not in the buoy, or vice versa. The other problem that we have is that, for instance, the events, usually they don't start at the same time, they don't finish at the same time, they are significantly different. So if you mess up everything, you compute average parameters, you are happy. But then if you want to go into details, then you have to work out all these things. So the first step, what we are trying to solve, is actually the combination of partitions, and also the connection in time to find the events with the same algorithm. That's what this algorithm is doing. It's doing all the thing at the same time. So trying to connect everything in time and the partitions as well, and then find the events and cross-assign events. And then, of course, the picture will not be so beautiful and so happy as Gigi was showing the one-to-one line. It will not be like that. We have seen it in more simple cases. And that's what we want to see, actually, to evaluate the model in more detail.
Okay, let's move to the last talk. Christian,
Thank you.
Thank you very much. So the last talk is Leandro Fernandez. Point to the screen, right? So you can place the pointer as well. Back. Yeah, and this is the pointer. Okay. So you can press. Yeah. You can point. Yeah. You can point to the screen. If not, then you can move it. You have to move it. There's the other one. Cool. Is the top one, right?
The first one.
Yeah, it's the top one. And it's back and forth. Okay.
Thank you, Nelson. Well, let's go with the last presentation. I will try to be brief in order to go to dinner, have a dinner. Well, this is a job we did in Ireland, University College, Dublin, under supervision of Professor Frederick Diaz. So we tried, or we set up the ST6 package of WaveWash 3. We already had some settings for XT4. What we did was validate, configure the XT6. When we had the XT6 configured, we compare with XT4 and took some conclusion. Also, we use some buoy data, and also we use other device, an ADCP. Here in this world, we didn't try to determine which package is better. It was not the intention. The intention was to validate XT6 and after use what we had, the XT4, in order to take conclusion. Well, this is the setting we use for the package. We use the way iteration. We use the DE8 approximation. As you can see there, we use the version of Seger-Vabanin 2015 for XT6 and the Haim et al. 2010 for XT4. This work was carried out under the project, the resource code project. What was the leader? It was a group of university working on the project, but we can say the leader was the IFREMER Institute. So we took the setting of XT4 for IFREMER. What we did is to validate the XT6 using the statistic parameter you can see there. It's the bias RMCSE correlation coefficient. But basically, what we did was to compare the probability density function of the significant wave height from using just the distribution, looking at the bias of the distribution. Well, this is the formulation, the equation that solve wave wedge. I will not explain in detail this because it was done by Alex Vabanin and also Eric yesterday. But here you can see the terms involved in the equation, where we have the wind input, the dissipation due to the bottom. And basically we validate the models using two parameters in both of them. In XT6, we validate the CTFAX parameter. This is familiar for user wave wedge users. So we use two parameters. In XT6, the CTFAX, this is the parameter that we use to, or is normally we use to eliminate the bias in the wind field. And the other parameter is the sin A0, the A0, that it controls the strength of the swell decay due to the wind effect. For XT4, the parameter we turn in was the Betamax is a very well-known parameter that is similar to CDFAX and XT6. And this new parameter, the swell F7, that is also related with swell dissipation. As I told you before, we already had the ST4 configuration. Why? Because we took for IFREMER Institute, this was the values of this some parameter they were using. The test we use is the T475. You can find the bibliography in Alday 2021. It's Matthias Alday, a researcher, former researcher in IFREMER. And they found these values. The only thing we did, we changed this parameter because we found they have other parameter in soil F7. But in our case, we found that this value matches better in our setting. I will explain you now. For the model, we have also, it's important to say that here, this configuration for XT4 and Ifremer was done taking into account an unstructured grid. Maybe for the reason we can it can be show some difference because we use an structured grid, 3 structured grids. So this is more or less no more or less, this is the setting of our grids and showing the position. Now we can, I can show you exactly more or less the position of the grids. We have 3 grids, a coarse one, intermediate, and the finest grid that is shown in that picture. The other setting is related to the spectrum, the number of direction and frequencies, 24 and 32. The result was taken every 610 minutes. We use the version of JetCo for currents. Well, also the aim of this presentation is to show some values we use because somebody several months ago asked me about the values I use to validate XT6. So for that reason, I'm going to show the comparison using the different values for this parameter. This tuning parameter is the A0. Remember, this is control the soil decay. Do it to wind input. These values, we get this value following some bibliography. Well, what we did here, we got the significant wave height parameter, and we did the probability. We get the probability density function, and we look at the bias of the distributions. Here you can see we use the 3 values that I showed before. And as you can see, at the peak of the distribution, we look at the bias. You can see, I don't know if you can see, but the values from bias is similar in all the cases. Also in the last one, 0.2, the bias seems to be 0. But what we watch here is the matching of the peak, the distribution. So we took that behavior, like you can see in the middle, in order to take conclusion about what value to use in the validation. In this case, you can see right there the CD fact 0.9. Why? Because we tried the default value for this parameter in XT6 is 1, but we noticed that with if you use 0.9, we got better results. So this work was done using the CD fact equal 0.9. This is the comparison with buoy, one buoy, the buoy A, and now is the same using the buoy V. Again, the same distribution, but now, if you can see, the bias in all the cases is similar. Also, the other parameter, statistic parameter, are also similar. They don't show significant difference. In this case, we found that this one, we watch this. By watching, we determine that this is the best match. So we did with several buoys, as I told you before, 6 buoys, and so we determined that we can use the 0.0980 value. This was for XT6. For XT4, these parameters, we did the same with these 3. They can make some suggestion.
Leandro.
Yes.
And this is something we will discuss also in Venice with Francesco. But you kept claiming that you tune the parameter to correct the bias of the wind field. How do you know that you are not correcting the wrong wave modeling? How do you know that the wind field is wrong and the wave model is perfect?
Yes.
Or the other way around?
Not in my case. Sorry, not. It was not a. I mean, I don't know. I just use suggested by the bibliography in order to improve the performance of the model. Where I see, for example, here, when I modify the parameter, I have different results. In this case, in statistics. So I don't know. I don't know about the wind. I have to trust. You know that several, you can get forcing from several institutions. So these parameters, in my opinion, permit that you can adjust the physical parameterization in order to get the results.
But this was not my question. Okay, we'll have time to discuss either tonight or tomorrow.
Yes.
Don't worry.
Sorry, I have the light.
Okay.
Thank you. That was a very interesting presentation. And I think to a large extent, you already know what next steps are to look at other parameters. And because I think this is more or less what we've been seeing. And to kind of circle back to something that Luigi said about, this apparent competition between ST4 and ST6 and why ST6 hasn't replaced ST4. Well, so ST4 was put into WaveWatch 3 earlier, of course. And so it's the incumbent, basically. And it's used now at Fleet Numerical, like U.S. Navy. And in order to replace the incumbent, you have to convince people that it's better. But I think we've been seeing mostly things like this where maybe it's a little bit better in places, a little bit worse in other places. And in order to convince the operational partners to replace it, it has to be basically a slam dunk. You have to really convince them, you know. So this is kind of the problem that we have. But yeah, and there are other complications associated, like with the wind field. So I think this, you know, one way to interpret this is the model doesn't matter, right? That it's just the winds or something else that maybe, you know, in the setup of the grid design or something like that. But the physics itself, yeah, right. Right, right. So maybe kind of a negative outcome if you decide, you know, either you can flip a coin. But on the other hand, I think it's useful to understand that at least both are performing well, at least for significant wave height. So that's useful.
Okay, thank you, Alex.
Yeah, it's a pity that this talk is at the very end and everybody is already waiting and counting seconds before the dinner, right? But it's an interesting.
I suppose Rodrigo has some announcements to us.
Thanks, Nelson. Thanks to everybody.